Hello and welcome. This is advice for how to complete Module 1 building basic circuits. One thing you need to know about Module 1 is that there is no programming involved. This module is designed to build up your confidence and to make sure that you're really good with breadboarding and circuit wiring. Now, in terms of if you're a beginner, I suggest you do every single tutorial. It'll probably take you at least double that, so about an hour and a half. If you are an intermediate user, as in you've done maybe a dozen Arduino circuits, by all means have a pick of the ones that seem interesting enough to you. Personally, the transistor circuits as well as the glow-in-the-dark are really, really cool. Finally, if you're an advanced user, you really don't need to learn how to breadboard. You can skip the entire module, but if there's something here that you find interesting, by all means, do it. Once again, I stress, the purpose of this whole module is only to get you confident with wiring circuits with breadboards. Okay, have fun with the tutorials. Hello and welcome. In this tutorial, we are going to be turning on this LED light and controlling it via a push button. Actually, you can see that on the circuit view right there. So, a couple of things we need to know before we get started. Our first goal is to have a look at how a breadboard works and have a think about how we can add power to the breadboard. You see these blue and red rails, they are consisted of these slots which are all connected. So we simply need to take a cable and connect one to the blue rail and one to the red rail. So red rail first. Red rail is going to need to go, I can put it anywhere in the red rail, and it's going to need to go into 5 volts. Now I happen to know it's in the 4th port here. I don't know if you have enough light to read 5 volts on there. I don't think you do actually. And the G&D is going to go into the G&D port right here and into the blue rail over there. So as you can see, it can go anywhere, but I'm just going to put it in the end to make it appear neat. Now, next up, I'm going to get my LED and point your attention, actually. Do you see the 2 legs? One's longer, one is shorter. You want to take the longer leg and bend it and then straighten it so that it looks like that. And then you take the longer leg, maybe just put it in a row and make sure the longer leg is facing the red rail. So the way we connect this LED, firstly we're going to do it wrongly, will be just to take, say, that negative. Dun, dun, dun. We've moved the camera a bit. So the blue rail is there. In fact, I can use these. These are like short wires. They look better on the camera. They make it more clear. So I can just take one of these and connect it. So now the short leg of the LED is connected, and if we connect the long leg to the red, we are going to see some fireworks, because actually there's going to be a bit too much current for the LED. In fact, it's already burnt. And I don't know if you can tell, if we turn it, ooh, it's kind of smoking. If we turn it sideways, and if you have a look, you see there's a bit of black in this LED. The reason I did that is for you guys to avoid ever powering an LED without a resistor. So there should be a new one where that one came from. There it is. Fold the leg again. And this time, instead of using a cable, we're going to use a resistor. So this is from the DF Robot kit. It is a 220 ohm, but any one up to maybe 600 is going to work reasonably well. But 220 makes it pretty bright. There it is, bright red LED. So what now? We're going to have a look at how this button works. We're just going to place it down over here so that it goes sort of across the bridge of this breadboard. It's right in there. And have a look at the button info card. Button. So the way that it works is that right across the 2 pins up top, let me try to point them out. I'll use this cable. This pin right here, in fact, let's switch to the breadboard view. So this pin right here and this pin connect when the button is pushed, but this one and that one are permanently connected, these two up top and these two at the bottom right here. So what we're going to try to do is make it so that this line that goes from the blue into the LED gets interrupted by the button. So I'm just going to go from blue rail into one leg of the button right there, and then from the other leg of the button into the LED. So I think the other leg is in number 6. Maybe I'll use a shorter wire. From 1 to 6. There it is. So right now when we push the button, there you go. And actually, I'll use a cable for this one. It would have also worked if we went across this way. So we connect it across this way. This would also work. And if it was across this way, it would be permanently on. So essentially, every time we build a button circuit, we can connect it 2 different ways. And the one that I just did, I think, is the neatest. So maybe just to sort of visually represent it better, I could park that in there. And that would be, dun, 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 pull that down, get the camera in a bit better of an angle. There it is. The LED pulls back. And there you have it. That is the button LED circuit. Now, I would like you to pause right here. And I will give you a challenge. The challenge is as follows. The DF Robot kit has a number of LEDs, some of which I've already burnt. Your challenge is to turn on 5 at once with just one button, using everything you've learned so far. The only limitation to your challenge is that you can't have LEDs share a leg. So you can't have 2 LEDs sort of entering one hole in the breadboard. So have fun with that and pause the video right now if you don't want to see the solution quite yet. Okay, so here is the solution. We are going to use the button to power one of the rails. We can either make it the blue rail or the red rail. If I just do it here, right now, this button is going to turn on the blue rail. And if I take any number of LEDs and place them into the blue rail like this, then you would need just to connect these LEDs to a resistor and the red rail, and they would be powered. So I got 5 in there. So I would need 5 resistors, in theory. So 1, 2, 3, 4. There are some right here. So if one works, they're all going to work. So if I go from here to the red and I press it, it's on. So I do the same thing. And I think I need one more. There you have it. The trick was entirely, maybe I should pull this out because it does nothing. Right now, the blue rail is only connected when the button is pressed. If this minus was where it normally should be inside the minus, they would permanently be connected, but now the minus only connects when the button is pushed. As you've seen the way the button works, we could have the minus in number 6 as well. Okay, there you have it. See you in the next tutorial. Hello and welcome. In this tutorial, we're going to use a potentiometer, which is actually a variable resistor from 0 to 10 kilo ohms, and we're going to use it to dim an LED. Now, in order to do that, I will jump into the breadboard view. And in order to do that, I'm just going to plug in the LED first. Basically, we're going to have one end going into the blue rail, essentially the minus. And for the plus, I'm going to have a 220 ohm resistor in the plus. Here we go. And there we have it. The LED is on. So what I'm going to do is I'm going to try to basically replace this resistor with a potentiometer. So the way I'm going to do that is I'm going to place this potentiometer in here. And the resistance, by the way, is going to come in between any 2 legs on opposite sides. Now, ideally, the LED would still pass through a resistor. So maybe I'm going to put this resistor out the back and then have a path go from the LED into the potentiometer and then into the 5V. So I'm just going to, in a way, guide the 5V towards the LED. It goes into the potentiometer there, and it should go out to the potentiometer. I guess we could try to move it closer. As I said, any 2 legs will... Oops. So there he is. That's not working. I guess the easiest thing would be to just use that really long cable. And these 2 are connected, as you can see. Now if I turn this, you're going to see slowly the LED, watch right here, it's going to get brighter. It's getting brighter. Now it's fully on. Off, on, and there you have it. That is the potentiometer working as a dimmer. It's all happening really in the lower third of the potentiometer range. Okay, so I'll just move the camera a little bit. As you can see, the potentiometer looks like that normally. So after you have found the optimal range you can leave it in, and you can adjust it by turning this knob. And just on the cusp would be about there. Excellent! See you in the next tutorial. Hello and welcome. In this tutorial, we're going to use a transistor to amplify the current inside the LED by passing it through our own body. So we're going to electrocute ourselves with a very small current and control the brightness of an LED using that. So let's first have a look at this transistor. I'm going to put it in here, and I don't know, let's zoom in. You'll notice, merge. Okay, so I'm sure that in this image right now, you can see the three legs. The first leg, that one, is called the emitter. The emitter is always connected to the minus. The middle leg is called the base. The base is going to control the current through the transistor. And the third leg is called the collector, which is always connected to the plus. So our goal is to get a current between the plus, right there, this red rail, through us into the base, which is then going to control how bright an LED is, depending on how tight we hold onto the ends of a wire. So let's get this show on the road. I will actually show you the circuit we're building. So right here, we're going to start by connecting the emitter to the minus, the collector through an LED to the 5 volts, and then we're going to put in these 2 wires. So I'm going to zoom in so that you can see what I'm doing. And here we go. Red or green LED? Red or green LED? I'll just go with red for now. So up top of that drawing was a collector from plus to right there. The minus, the emitter, is connected to the blue rail. So I think I got it. Let's see. Yep. And all we need now is the 2 wires. So we're going to go the blue one to the base, the white one to 5 volts. If you touch these 2 wires together, you're going to burn out the LED at the moment. So do not do that. But if you touch them to your fingers, look at that. You control the brightness on how tightly you hold them. And if they both go into that, if both of these guys sort of go into the finger, I'll try to get the view good for you guys. Interesting. You still have to press in. So the very outer layer of your skin is not that conductive. But if you hold tight, there you go. You get the effects. So let me just try with a green LED for fun. Will it work as well? Will it be brighter? Green is the color that humans see the best. So always fun to experiment with red and green. All right, green. Not as bright. Not as bright. The red was brighter, definitely. Okay. So next up, I just want to demonstrate the same principle with a variable resistor. So I'm just going to plunk this guy in anywhere, and I'm going to try to make the same circuit flow through this. This is 10K, whereas the resistance in my body is huge. It's like probably measured in mega ohms. So I'm going to get a resistor in to connect that to the emitter, so we limit the current in the overall circuit so we don't burn the LED. And we're now going to flow the current through this guy. I guess I can just get this guy into there. We don't have to use the long wires. I think it's easier for you guys to see when I use the short little ones. And this, well, this has got to go from one of the legs, either one, into the base. There we go. So, in theory, we should be able to dim it, although it's going to have a very narrow transition area. Yeah, right there. dimmed, bright, off, middle. There it is. So right now we have used a variable resistor to control the brightness of an LED through a transistor. And it's, as you can see, the effects are much, much stronger. Even the slightest of turns has a big impact. That was very slight, and this also is barely there. And we go basically from 0 close to full brightness. Okay, now you guys know how to use a transistor. Now, one last note, perhaps, just in case you're gonna go from here to try to construct more advanced circuits. Let me go back to this view. Make sure you look at the transistor data sheets, and what you're gonna find is that they behave very interestingly. They're almost a little bit temperamental. The transistor we got in our hand has roughly a gain, an amplification effect of 100. That is at 10 milliamps and 1 volt. So we don't even have information for 5 volts, but I think it remains reasonably constant. 10 milliamps is a reasonably bright LED, but it goes down to a minimum of 30 and a maximum of 300. So if you want precise amplification, you're really going to have to, pull out that voltmeter and do some testing. But if you just want to amplify a current and control it using something like this, then, your standard transistors are the way to go. Okay, that's it. See you in the next tutorial. Hello and welcome. In this tutorial, we are going to create a super amplifier. This is also called the Darlington transistor, and it consists of basically 2 NPN transistors. We're going to use the 2N3904s that we used before. They have a gain of 30 to 300, standardized at 100. Now, what the super amplifier, or the Darlington amplifier, what it does is it gets these 2 transistors lined up in this configuration so that the current going through the base of the first gets amplified, say by 100, and then that amplified current goes into the base of the next one and gets amplified again, so by 100. So we're going to get, 10,000 or 10,000 plus, somewhere thereabouts, amplification. And let's zoom in on the breadboard and have a think about how we can make that happen. So, I'm just going to place 1 transistor down, and then I'm going to look at the image and have a think about it. So they're going to have a joint collector. So the collector is sort of the opposite. It's sort of the bottom one right here. That is the collector. So that guy is going to be joint, and then the base of this transistor is going to go into the emitter of the other one. So we're going to have, there's going to be a skipped leg, something like that. And there it is. I don't know. I think you can see sort of the way the legs lined up. I'm going to bend this downwards. It's just about shown sufficiently. So I think the base, let's first join the collector. So we're going to go from, that's the collector, that's going to go into the 5 volts through an LED. And the emitter, which is the only loose emitter, which means it has to be that one there, is going to go into, in fact, maybe I'm just going to use one of those blue ones that we had before. Will it reach? No, it won't. What about this one? And And the base is going to be right here. So if you're looking at the LED, any current that's going to flow through the LED has no power source. Essentially, it's going to be electrons because the current flows from plus to minus. That means electrons are going in from the minus terminal into my body, and that flow of electrons will be amplified by like 10,000. Have a look. There it is. I don't know why it's pulsing. Quite interesting. I cannot see any pulse, but there is one. I can see it on the screen, and my own eyes tell me that its light is relatively constant. But that's pretty amazing. And I think something happens even if I just touch the wire on the outside. So there you see it. Highly, highly interesting. This is current that is going from the breadboard into my body, just a few loose electrons having that effect multiplied. And this is how antennas pick up radio waves. Essentially, they go through amplifier configurations similar to this one. So very, very slight electrical fluctuations that, are essentially all around us get amplified by, tens of thousands, even millions of times, and they get processed into signals. So there it is. It's a lot of fun to play with. Quite fascinating, really. Okay, bye-bye. I'll see you in the next tutorial. Hello and welcome. In this tutorial, we're going to create a glow-in-the-dark circuit using basically this, a light-dependent resistor. And we're going to put it in a configuration with a transistor and a potentiometer, and we're going to have a voltage divider. Now, the best way I can possibly explain this is with some images, and it is genuinely tricky to explain, but we're going to give it a go. So here you are current, and you're trying to get to Earth, basically from plus to minus. And this is what's going to happen. By default, let's assume this line is blocked, the transistor is off, and the current is going to flow this way. And at this point, it's going to split. It is going to split, and I guess I can call this into I1, and we're going to call this I2. Now, this is where the interesting thing happens. With this being a light-dependent resistor, when you shade it, when it has less light, I1 goes up. And when you shine a light on it, the I2 goes up. So therefore, if you can get this guy turned to an amount where when this is shaded, I1 is such that this light goes on, you can achieve this equilibrium. So after we build it, we're going to have to be adjusting this 10K. And if I'm right, we're going to be in a state where the adjustments can make the light permanently on or even permanently off if we go all the way up to the 10K. So this should be interesting. Let's build it. Merge. Okay. So what are we going to put into the breadboard first? I guess we can try with this transistor. And the transistor, get rid of you. So the transistor has the emitter, which is the top pin. It is connected through the variable resistor into the base. So if I was to take one of the, I don't know, the base would be this pin right there. And if I was to, no, wrong pin, base. Now I would need another little red one. some wires. Well, yep. So what we've got done so far, if I merge, so far we've connected this line. So let's see what's next. Next we're gonna get the middle leg connected to the LDR, connected to the minus. So right now we've done this whole back end. So now we can connect the collector, and the collector is going to go through a resistor into the LED into the 5 volts. So the LED plus in the 5 volts right there, easy. Collector right there. And last but not least, we just got to connect the emitter into the minus. And this should be the easiest one yet. Okay. EBC. Aha. This guy's one off. Let's see. Aha. There we are. Off. Always on. Always see. Always on. Always off. And let's see if there's like a happy middle. Ha. Pretty easy to achieve, actually. So there is the sensor. In fact, maybe I can just move the camera a tad so you can see the sensor better. That's the sensor. Watch me shade it. Shade. In fact, I'm curious if something as thin as this wire, yeah, even putting a wire on top creates enough shade. And there you have it. A very easy to build, purely circuit-based, glow-in-the-dark circuit. Okay, see you in the next tutorial. Hello and welcome. So in this tutorial, we're going to create an AND logic gate. And an AND logic gate is one of the main subcomponents of all microprocessors and microcontrollers, such as the Arduino that we have right there. So essentially all it is a circuit where you have two inputs, which we're going to have buttons with. And so our two buttons, you have to press both for the light to come on. In a way, it's two input signals, both of which need to be on for the third output signal to go on as well. And the reason why I wanted to construct some of these logic gates, and the reason why I'm trying to do them using transistors, is because all complex sort of logic units, be that from the calculators that you use all the way down to the computers where you see this, are made up out of this type of stuff. So let's just set one up. And what I mean by that is get this button in across the breadboard and have a 10K resistor connect to one side. So this would be the input. And this would go into a leg of a transistor. In fact, you guys would be seeing this a lot better if I maximized it. So that transistor goes such that the base is on the leg of the button, and then it's gonna go to a LED, which goes through a resistor. I guess the easiest way to put it would be like, that's a 220 ohm. right there, and we can have our usual trusted red LED to go in like, oops, long leg needs to be there actually. So when I push this button, essentially this minus right here, if that went to the emitter, well, the collector, we're facing away. So this should, in theory, work. Yeah. And so all you do is a cycle of 2 of these, which shouldn't be that hard. I guess I can... Dun, dun, dun. So repeat what we just did. That wire goes there. Emitter base collector. We need a button. The button goes on to the base with a 10K input. And the collector is going to go and connect itself to the plus. Dun, dun, dun. And I guess the simplest way would be to take this breadboard wire to the plus. So, in theory, pressing one button, you can almost see a little tiny amount of light. That's how much current leaks in. For the other one, you see nothing. But when you press both, it goes on. One, nothing, both on. One, both. So there you have it. That is the AND logic gate. Hello and welcome. In this tutorial, we are going to build an OR logic gate. Now, what we have on the board right now is an AND logic gate. We press one, nothing. We press the other, nothing. We press both, the light goes on. So the OR logic gate essentially means we press either of the 2 buttons. So rather than build everything from scratch, I'm just going to pull out the entire configuration for the second button and just create one sort of independent button that will turn this guy on, which is going to be my first logic gate. Let me grab the Afrobot jumping leads. All right, so we're gonna get this EBC, that would make it the collector, connect that to the plus, and technically, yep, we're good. So we essentially need to build another almost independent circuit that's also going to connect to this LED. Shouldn't be very hard. The button goes in, the transistor facing away. The transistor needs to be connected to this leg of the LED. In fact, we have the perfect length right here. Come on. Yes, we can. Get in there. 1, 2, 3. No, we need to go one up. That's where the LED is. So we can then connect, I guess I'll have another red cable so that you know that it's connected to the plus. We can connect that guy to the plus, and we only need the 10K activating resistor to go into the button. So I don't know if these wires are obscuring too much. I think you can still see all the circuit. In fact, let me give you the large view. These are connected both into the collectors. So the 2 red wires go into the collectors of both the transistors. This red wire goes into the emitter of this upper transistor. So all we need is that 10K, which is gonna go right there into the plus. So the OR, essentially, whether they're both on, the output is on, or whether one of them is on, the output is on. Let's have a look. Works, works, both shall work. There you have it. That is the OR logic gate. Hello and welcome. In this tutorial, we're going to build a NOT logic gate. So the idea here is we have a very, very simple circuit. When you push the button, the output is 0. When you don't push it, the output is 1. So essentially, we simply got to put in an LED and turn it on initially. And then we're going to have a bypassing circuit that's going to divert the current away from this LED when the button is pushed. There you go. So that would be a pretty straightforward part 1 of the circuit. Now for part 2, we would have to put the collector of a resistor right there, right in to the same port. So the collector goes right there in between the resistor and the LED. The button is going to go with one leg into the base, then the 10K resistor is going to go into the other leg, so that pressing the 10K should turn on the base, and finally you make the bypass complete with connecting the emitter into the ground. So that should do it. And that's easy. Push the button, LED is off, otherwise the LED is on. That is the NOT logic gate. Hello and welcome. This is the module introduction to basic input-output circuits and programs. So just like the first module was only about breadboarding, this module is essentially all about programming. The circuits are as simple as I could make them. They only use LEDs, resistors, and push buttons. So the journey begins with just a basic LED blink circuit, which is then added, which is then improved with having a variable control the blink rate. Then we introduce some random functions and have LEDs blink in various random ways, be that random delays or a random choice of an LED. And finally, we add an input, which is a button. And then we use the button to alter the way in which LEDs blink and the speed in which they change. That more or less summarizes what you're going to learn, so I shall see you in there. Hello and welcome. In this tutorial, we are going to begin with programming. We'll be taking a simple, humble little LED here and making it blink using an Arduino program. Now, let's get into it. You will notice, however, before we even start, that there is a blinking LED on the board right here. I'm pointing at it. And that is a sort of native LED that exists on Arduino. I believe it's tied in with pin 13, even though you can access it via saying like onboard LED or just calling out pin 13. So first of all, I may just try to get this guy to blink at a different rate. So let's start a little program. We can call an LED. We can start by declaring it. Call it LED on board equals to 13. So from now on, every time I say LED on board, the Arduino is going to receive 13. And so we can say pin mode. So we can either write 13 output, or instead of 13, we can use LED on board. Now, LED on board, in a way, is easier to read if someone else were looking at our program, so we're going to do that. Then we're going to digital write LED on board, comma, high, delay, and we're just gonna make it blink fast. We're gonna delay, I don't know. Actually, let's just go something big. 2 seconds, delay 2000. Then we're gonna basically repeat this code, except we're gonna make that low. So it should blink even slower once this program is uploaded. Arduino Uno, port that one. We're just gonna save it as today's sketch. And there it is, blinking more slowly. And now we can just try this out. Very interestingly, this is the only pin that can be, where you can use an LED without a resistor. There's also a resistor inside pin 13. So if we get the long leg inside pin 13, in fact, I'll be looking at the camera here for guidance. 8, 9, 10, 11, 12, 13. If we get this guy in, he won't burn up. And see, these two are on at the very same time. So, in fact, I think getting a little bit of resistance and getting this guy to be a bit more faint could also work reasonably well. So I guess I can just get a cable into 13, 8, 9, 10, 11, 12, 13. Dun, dun, dun. Get a resistor in there. So right now the resistance is like 400 ohms. There it is. Still pretty bright, but at least right now we can see this little guy right here. He's not obscured. So I want to do a little bit of an experiment. And the experiment is this. I would like to try to get this light to blink so fast, or find out the exact rate at which it's blinking and we don't notice it. So this here being milliseconds, we can try, obviously at 2 seconds we notice it. We can try 1,000th of a second. Dun, 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 dun. Yeah, I definitely can't notice that blinking. So that's a speed too high. Now let's use this to discover the sort of number of blinks per second. That is like the refresh rate of the screen you're looking at right now, which is either 50 blinks a second or 60. So let's declare an integer and call that frame rate and make that 0. Actually, I'll have a think about it. So the delay here should be like 1,000 divided by frame rate. So let's say something is meant to happen 60 times a second. However, that event takes place in 2 of these delays. So we actually are going to have to make that even faster. So let's think about how long this blink takes. A blink is a light on and a light off. So this whole blink is going to take 2 portions of this. So basically in, 60 turns, this whole thing is going to happen in 2 seconds. And we want 60 blinks to happen inside 1 second. So I need to divide it like that. 2 times frame rate. 2 times frame rate. So let's test this out. So frame rate is right now 0. Let's try frame rate, something that we should be able to see. 5 blinks a second. Let's see if that actually works. I believe that this isn't 1,000 divided by 2 times frame rate. I think that this is 1,000 divided by 2 times the frame rate. So that, let's have a look if this was a bud mass issue. Let's try that again. We should be looking at something like, yes, that looks like 5 blinks a second. That looks believable. So if the screens happen at, 30 a second is already something reasonably fast for the human eye. Pay attention to this. That is fascinating. That is fascinating. What you guys are seeing right now, because this video is being recorded at 30 frames a second, is a really slow blink. I'm looking at it on the screen right now, but what I am seeing is a light blinking so fast I can barely perceive the blink. Let's see what happens if we go frame rate 50. Yeah, I can't tell. However, you can. Again, this is a very, very interesting effect. What you're seeing in the video screen and what you will see when you put this program in are 2 different things. I cannot perceive any blinking whatsoever, and the screen actually, like I'm looking at the video footage, the same video footage you guys are seeing, and you can. So this is an interesting tutorial in a sense that this would even be different for individuals. So at 40 I can perceive perhaps some type of vibration. I wouldn't even be certain if this is blinking. At 30, I can perceive vibration. And at 25, I can definitively tell that it's the LED is blinking. So this little experiment, which is going to look completely different to you when you're actually looking at an actual LED as opposed to the screen of a camera that's recording in 30 frames a second, you're going to discover at what point you begin to perceive the blinking. And sort of the universal threshold where pretty much everybody cannot perceive blinking is at 50 frames per second. So there you go. Do this and have fun with it. Hello and welcome. In this tutorial, we're going to use 4 LEDs and control them to create different patterns of light and even sort of random patterns. Now, the circuit is here on the board, and just like we did in the previous tutorial, we're just going to connect 4 of them initially through a resistor and then into the earth. So I guess if the first LED here is a 6, I can go in and build that one. So we declare it int, we can call it LED1 equals to 6. We can pin mode here, pin mode LED1 is an output. We could have put 6 instead of LED1, and digital right 6 is high. So here we go. Where is pin 6? Right there. Let me merge this for you guys. So pin 6 goes in there, that goes into the breadboard, then that goes into a resistor, and then that goes into the minus, which hasn't been moved over. And I think if I upload this, that light should come on. Brilliant. And we can kind of face it to the camera. That's our start. And if you want to be, I'm going to actually try to be a bit neat for you guys and try to make everything ultra visible. I'll take this out, And I'm going to do this instead. I'm not going to be doing this in future tutorials. I just want the first couple that have breadboarding to be really clear. So what you can do is if you have, if you've got your arrangement here with the Arduino and the breadboard or solidly in place, you can put the resistors in first, then the wire. You can put the wire going into the resistor. What I normally do for myself when building circuits, I basically use these really long wires, but for visual purposes, we're gonna leave it like this. So I will now wire up the rest of the LEDs. Dun, dun, dun. You can go in, it doesn't really matter which holes they go into. Yes, you can go there. You can go there. Dun, dun, dun. It is. So and 6, 8. And the last one is going to take some stretching. Oh, there it is. 6, 8, 10, 12. Dun, dun. So let me have a view of the code now. Okay, so right now we can copy and paste 2, 3, 4, 8, 10, 12. And for the teachable moment, if we declared like LED 2 as output, we should still see that LED having a little bit of power. Essentially what that output does is supply the LED with power. It kind of looks like it doesn't work. But all it is that LED has now got a microscopic amount of power compared to when you declare it as an output. That's what the role of outputs are. So 1, 2, 3, 4. And 6, 8, 10, 12. So this should turn them all on. And that's pretty good. So interestingly, these red ones, to me they all seem equally bright, but to the camera the red ones seem less bright. So let's see what we can do here. Do something interesting. Put in some delays. So maybe turn them all on and then turn them all off. And then put this to low. 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 So they'll all go on, they'll all go off, and we can put a delay. Delay 1,000. Delay 1,000. Now they're blinking like that. And you can do all kinds of various things here. For example, that's going to have the lights come on one at a time. Watch that. 1, 2, 3, 4. and then they're going to go all off together. And we can also have all kinds of patterns, the 2 right on and the 2 left off and so on. We can have the greens and the reds alternate. It doesn't really matter. And another thing, since you declare these names, and the reason why we put the names in is because when the programs get large, you may not know, for example, what 6 is, what 8 is it a light, is it a buzzer, is it a button? So generally speaking, we would be replacing the numbers with the allocated names. And as you can see, I'm just literally pasting in the names, and that should be a completely identical program. So that was a sloppy mistake on my part, which turned into an awesome teachable moment, and I'm kind of glad I made it. So now I need to make sure the light's okay. Now I'm gonna show you a really neat trick. I'm gonna turn one of these lights on, and I'll pick a random one. Check this out. So if we're gonna turn delay 1000, so we're gonna use the random function in Arduino, and that's random, and you inside the 2 brackets pull in the range, and the range should be 1 through to 4. And just for fun, now I don't know if that includes the 4. We're gonna find out really quickly. In many programming languages, random includes that higher number, but I think in C, it'll be random between the first 3 lights. So let's have a look. Delay 100. So we should have like 10 times a second a random light go on. Oh, what am I doing? We don't have lights. We don't have lights 1, 2, 3, 4. We have LED 1, LED 2, LED 3, LED 4. So I could basically, since they're all between 6 and 12, I could write 6, 12, and we're gonna have an effect. Have a look. So the 4th one never seems to be coming on. So if we did 13, I believe that any of the 4 lights could come on. Yeah. There you have it. So I believe perhaps we could do a much more interesting job if we randomized, I guess, all of them. Let me show you what I mean by that. Instead of high or low, you can use 1 and 0. So you can go random 0, 2. And this is going to give us 1 or 0, because remember, we tried. When we put the 12 there, the 12 didn't come. And this could be LED 1. And we could copy this line for all 4. And that should give us a pretty cool, by the way, instead of turning it off for a second, watch this. This should be pretty fun. Maybe 200 would have been a nicer delay, so it's 5 times a second. The status is going to change. Have a look. And there you have it. What we have generated is a pretty cool random light pattern. So just to reiterate the lessons of today, when naming variables, you can, it doesn't matter like the fact that this is text. This is just a variable name, but you say that it's an integer. So that's being a round number and you refer it to a pin. So now the number 12 and LED 4 are essentially interchangeable. You can write 12 or LED 4 to the compiler. It's as if you're writing the same thing. We have a random function, and the random function generates a random integer, and it generates it between the number that's first before the comma and the number 1 lower than the high number. So in this case, it's a 0 or a 1. And you could have had a random delay here. You know, we could have had random 100 to 600. And that in itself would make a random delay, which would make that look even more, would require a comma. So that's how the random works. So there you have it. And one little trick for future reference, Control-T automatically indents everything. Excellent. I will see you in the next tutorial where we are going to introduce little push buttons that are going to control the light patterns. Bye-bye. Hello and welcome. In this tutorial, we're going to try to get our 4 LED setup controlled in some way by the press of this button. So I'm first going to go onto the breadboard and install this button into, say, I don't know, pin 3. I'll merge this. Let's have a look. We just place it like so across the bridge. We're going to actually need to have a powered up red rail on the other side. So in you go, son. Come on. Surprisingly hard. There we go. Didn't really upset the order of our LEDs. So we're going to need to go into one leg of the button from the red rail. And in the other leg, well, we're going to need to sort of ground that. Now, we can use any resistor and put that resistor in the GND right here. Now, if we did a straight up wire instead of this resistor, what would happen would be a short circuit, which would be pretty dramatic. The Arduino would go off. Not good. So now we can simply take that leg into 0, 1, 2, 3. And there we have it. I don't know. This is a lot of a wire. Maybe I can just bring it down like that. There you have it. So now that we've installed a button, time to code it in. Let's merge that. Here we have our LED panel code. I guess we can add a button. Int button equals to 3. We can pin mode. Button as input. And decide what we want to do. Well, let's just as a test case turn on all the turn all the LEDs on if the button is pushed. How are we going to do that? Well, simply inside this loop we can forever check if digital read of the button, if that equals to high, then open bracket, close bracket, right there, we can do whatever is inside these two curly braces. So here we can have digital write LED. This digital write should turn orange, I think. The digital write. Yeah. LED 1 high. So we can turn all of them on and make that 4, 3, 2, 1. And if we don't turn them on, I guess we can do an else statement, open bracket, enter. The new bracket just gets drawn for us nicely, and we can, I guess, copy all of that right there and just turn them all to low. Now this is just a test case. We can do a lot more fun stuff. So let's upload that and see what happens. What's not declared? Button. We're gonna need a U. Alright. And for some reason, LED 1 is just left out of the party. LED 1 low, 1, 2, 3, 4, 1, 2, 3, 4. Yeah, I wouldn't know. Let's just, I don't know, for curiosity's sake, I will test this. Make it 5,000. Maybe the LED died for mysterious reasons, but that LED, if it comes on... Alright. Oh! Now it works. I have no idea. Okay. As you can see, sometimes the errors we get just don't seem to make much sense. So let's see what else we can do with it. I guess we can create a Boolean. And I think we can call this Boolean random. We can call it rand state. And we can call that equals to true by default. And then inside this if statement here, we can just use that to change this rand state. So we can say rand state equals to exclamation mark rand state. Now in C, Arduino, and a lot of other languages, this guy right here actually makes a true statement false or false statement true. So right now, when we press the button, rand state is going to switch from true to false and from false to true. So we're going to need a separate if statement right here. And I guess, you know, for simplicity's sake, we can just copy this if. If rand state double equals to true, then we can random 0, 2 and copy this guy over all the highs. And if not, well, if not, then I guess we can just turn them high. So this, in effect, is going to give us two potential states. The way that I see it is if I hold a button down, all the LEDs are going to dim at the moment, because if they're randomly turning on and off, but they're doing this at like thousands of times per second, that's going to be imperceivable. So we're going to need like a delay, a small one. Let's have a look if this compiles. If rand state double equals to true. True was not declared. Well, I guess we can always try 1 and 0 for true and false, but does Boolean work? Would true turn blue? Nope. I don't know. let's try this. Well, clearly 1 and 0 seem to work for true and false. So all the lights are on, and this makes them random. That is pretty terrific. And we can make it... Oh, and just to make things interesting, imagine that we had some sort of delay variable, and we call that int delay. Delay equals to int, I guess we can call it dy for delay, and we can make that start at 500. And we can delay dy, but we can also, while pressing the button, make dy equals to dy minus 10. So that's going to decrease the delay. So the longer you hold the button, the faster the blinking is going to go. Let's have a look if that works. I think so. And eventually the dy has hit 0, and essentially that creates an error which leaves us in a still state. So when dy gets negative, we have something interesting happening. So we can also have some other way of handling that, and just say if dy equals to 0, if dy double equals to or is less than 0, then you set it dy equals to 500 again. And let's try this again. We can try, I don't know, see if the delay is going to get smaller and smaller. And I think it should continue from that sort of high-speed switching, high-speed switching, high-speed switching, high-speed switching, flying, fast switching, and now we're back to the half a second. So there you go. It works pretty well. Now, in case you wanted to see that in action, we can do something called serial.print, or serial dot, we need to begin the serial. Now this allows us, for Arduino, to receive a message, essentially. It allows us to receive a message from the Arduino. So the message that we can receive, for example, could be the present state of the variable dy, so the present state of delay. So in order to do that, we just simply, while this is all happening, as the delay is being executed, we can serial print len. ln stands for printed in the new line, dy. So right now, after we upload this, I think semicolon, after we've uploaded this, we can have a look right here. So it prints 500. This is our present delay. So we had to press on here, that's the serial monitor. And as I push this, you're going to see the delay falling. And eventually, it's going to fall down to something pretty quick. And the laser, you know, this is happening ever so quicker as we move towards 0. So right now, there's like a 1/10 of a second between delays, and watch this. And we're back, I think, at 500. Now, we could have done something that I consider cooler. If it's less than 0, we could have kept it at 5. So, or we could have even said, if it's less than 5, just make it 5. And I think this would have worked all the way down. So one more time, we click on that. And the delays between just get exponentially briefer. We're waiting for half a second initially. Now we're down to a third of a second. I reckon. And see, you can sort of pause it. I lifted my hand. I think it does the auto scroll, so you should be able to see the bottom. And this crazy blinkiness is happening, and it stays at 5. That's pretty cool. And I think 5 is perhaps a bit too fast, but I like this effect. Okay, so that will be all for that. You have, in this tutorial, learned how to, 1, install a button, 2, use it to control some LEDs, and then we have looked at an internal variable into the program that's going to control the delay as well as the random effects of individual LEDs. So in the next tutorial, we are going to install multiple buttons, and they're going to control what a little buzzer initially and potentially a little speaker does. See you then. Hello and welcome. This is the module introduction for Module 3 Analog Circuits. So, in this module, we are going to cover analog circuits, which are different from digital ones in a sense that with digital, you receive an on and off input and you put out an on or off output. With analog, the inputs and outputs are measured. In the case of Arduino, they're measured as some fraction of 5 volts on each pin, which are represented in our programs as a number between 0 to 255 for outputs and 0 and 1023 for inputs. So we're starting off with a classic configuration called the voltage divider. And this is how pretty much all analog, well, a majority of analog circuits are wired. If you have some element that's a measuring element whose resistance varies with what we're measuring, like a thermistor or a light-dependent resistor, you have to set it up in a voltage divider configuration. So this is what we do. We build a voltage divider with a potentiometer, and then we use a photodiode as well as an LDR here to just see how it can be used to measure light. We create a manual glow-in-the-dark circuit. We apply that to a theremin. But we also look at different analog circuits like the LM35 temperature sensor, which doesn't work in a voltage divider configuration. We also play around with colors. We get an RGB LED mixer with 3 different potentiometers to control for red, green, and blue. We recreate something called a Maxwell wheel, which you're going to see about, and we really get fancy with microphones, creating clap switches, double clap switches, which are really tricky, and a sound reacting circuit, which kind of has music downs, dance, the lights. Okay, that's all you need to know for the introduction. Now get in there and do the tutorials. Hello and welcome. In this tutorial, we are going to create a voltage divider circuit. Now, this is a pretty important concept in electronics, and I'll first try to explain it on the schematic, after which we're going to build a circuit and illustrate what I'm talking about. So imagine that you have a sensor, and that sensor is, an analog sensor which is going to give you a value between 0 and 1023. Now, you can think of 5 volts as 1023, and you can think of G and D as 0. So you set up a circuit that looks like this. A device that varies in resistance connected to the 5 volts, and a device that doesn't vary connected to the GND. By the way, you can do this upside down as well. We're going to do it in both directions. So as you can see, when this variable resistor, when this is really low, or let's say it's 0, you're going to be connected directly to 5 volts. You'll be reading 1023. But this here being a 10K potentiometer, if this was 10K, then this 5 volt would be divided 2.5 volt here and 2.5 volt here. So this reading that we're going to be having is some value between like 500 and 1023. So that's what we're going to try to achieve. And then conversely, we're going to switch these around, and we're going to see if what we get is a value between 0 and 500. So let's get started. Let's start with just getting an analog reading. So I'm going to put this into A0, and I'm going to leave it sort of hanging out. I won't even put it into the breadboard. I'll leave it hanging, and you'll have a reading, and it won't be a meaningful reading, but it'll be a reading. So I'll just stab it in. There it is. So let's open up a program, and we're gonna have, a variable, call it integer reading, and we're gonna initialize that to 0. Then we're going to pin mode A0 is gonna be our input. And here, we're going to say reading equals to analog read A0. And then we're going to print it. Serial dot print ln reading. Now this is not going to work yet because I haven't initialized the serial, which is going to be here. Serial dot begin 9600. Okay. Oh, we need a delay. Delay anything. 50. So 20 times a second we should be getting an analog reading. I'm just gonna save it anywhere. And hopefully, when it's done uploading, we can check the serial monitor right here. Boom, boom. So as you can see, it's sort of like giving you random values. And if I take it into my hands, it's sort of oscillating between 1023 and 0. It's chaotic. But if I were to put it into a minus, it would be straight up 0. If I were to put it into 5V, it would be straight up 1023. So let's check our initial theory. We're going to get a variable resistor to go into the 5V. And there he is. I mean, we just grab a wire now to connect that, and we should be on a 1023, no matter how much I turn this wheel. It's constantly 1023. Now watch this. This could be interesting. I think this is a 10K resistor. You can always take a little, well, we're going to know immediately. Because if it's not. Okay. So my theory was it's going to go from about 500 to all the way to 1023. 514, 1023. So there you have it. And if we were to pop that around, so have it the opposite way, so say connect that directly to minus, it would go from 0 to 500. Boom, boom. And connect that to that, and then connect the 10K to... So it would top out at 500 and go down to 0. It's kind of more convenient to do it the other way. It looks neater, so I'm just going to control it from that 500 to 1000. So let's now use that to write a value to an LED. And you're going to observe something interesting. I can't wait to show you. So as you can see, the analog read goes between 0 and 1000. Next, we're going to use an analog write. And we're going to need this LED for that. We're going to put the LED here. That's an LED resistor. We can put it anywhere into the breadboard. And we can get a cable into the first available PWM port. So that's the one with the squiggly bit right there. That's a 3. 0, 1, 2, 3. So we've added an LED, so I can call it int LED red equals to 3. And we can set it pin mode LED red. That's an output now. And interestingly, right here we can analog, right, LED red, wait, LED red, we're going to write reading to it. So whatever is the value of our reading, that's what we're going to write to our LED. So we're going to write 514 right now. Semicolon. I don't think I've ever done a program where I didn't forget a single semicolon. All right, let's have a look. 514, oh, this thing's not, ooh. So 577, and it's getting stronger, and then it drops to 0. Look at that. So this is where you find out the interesting fact that analog read goes from 0 to 1023, but analog write goes from 0 to 255. Heh. So we somehow need to transfer a value that's between 500 and 1000 to 0 to 255. So I guess we can minus 500 divide by 2. I guess we can have int LED value equals to 0. And then we can say LED value. And I guess equals to whatever is in here, we're going to convert it to integer. So we're going to go reading minus 500, and if 514 was the minimum, so it's gonna stay maximum, it's gonna stay there, it's gonna process the brackets first, I don't know, and we're gonna print LED value because at the end of the day that's what matters. So serial print. I think we're going to have a working potentiometer here. That's going to take our LED from nothing to something. Okay. So, moment of truth, 137, pretty low. So, the lowest, that's 261, and, oops, 7, 12. So, if we crank it going this way, we are going to go past 255. 261 is still strong. Ah, because we're still writing the reading. We should be writing LED value. I was confused looking at those. And I think it's still going to have a bit of an error at the very end, which we can easily correct, but let's observe. 137. Perfect. That's practically 0. And now we crank it up and up and up. And when you go all the way to the end, you get to 261. So you've got just a bit too much. And if you made this, I don't know, divided by 2.1, you would probably sort out the problem. You're going to see it right now. I mean, the goal is to get to like 250, 249. Perfect. Whee! That is a perfect LED dimmer. And on retrospect, it would have been easier to organize if I had, where is my schematic? voltage divider circuit. If I had simply done this the other way around with the potential resistor being attached to ground, it probably would have been a bit easier, but it doesn't matter. You just work with the range you have and you use some simple algebra to turn that variable resistor into an LED reading that is roughly between 0 and 250. Excellent. I hope this was educational. I will see you in the next tutorial. Hello and welcome. In this tutorial, we're going to use a photodiode or a light detector, and we're going to use it with the voltage divider circuit you see on your screen to make a self-calibrating glow-in-the-dark circuit. Now, this isn't particularly difficult. In effect, it uses the same code that potentiometer uses. As you can see, I'm going to turn this potentiometer, the light's going to get brighter, dimmer, brighter, dimmer. If I take it out and replace it with this photodiode, clunk, there's going to be some type of an effect. Dimmer, brighter. As you can see, if I touch it, there you have it. I think it works better with the negative plugged in, the shorter leg plugged into the positive. As you can see, the variances are getting wilder. So I'm going to leave that in, and I'm going to start thinking of ways that our light here, because it's in sort of bright conditions, is going to be at 0. Let me have a think about how we can get that done. Now, when we start, we can take a light reading, and quite simply that reading, at that light reading, the LED should be 0. So I guess we could call it like default value, int default val. And we're going to call that, we're going to set that default val to 0 initially. And when we start, I'm going to say default val equals to 0. So that way, maybe I can also, give it, just make a small delay at the start so it doesn't quite get too much of a kick, so to speak. So right now, we're going to record this default value. And the goal is, inside this analog write, that we're going to have this reading, this right there, that's going to turn to 0 or 1 or really, really low when the light conditions from the moment the circuit went on remain the same. So I'm just going to have another variable here, int, I'm going to call this LED power. And we're going to set LED power to 0. And right here, since LED power is what we're interested in, we can print that. And we can write that in here. Now, what is LED power actually going to be? Well, the neatest way to do it is if we just have a set of readings here. When I shade that, my readings shrink from 900 to 300. And if I turn it the other way around, just curious. It's 20 to 4. It's definitely bigger if I start in reverse. So from 900 down to the shortest it can be is probably about 300. And when I let go, it's 900. So LED power can be reading minus default val. And just in case we're afraid that this is going to turn out into like a negative value, I can take the absolute value of that. So you're going to see what this LED power is when we run this. But my prediction is that when this code uploads, that LED is going to go off. And when we open up the serial to see the LED power is going to be like really low. I mean between 0 and 3. Okay, so far so good. Yeah. But watch this. Some shade, it gets brighter, 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 very bright. So it really is that simple. Watch what happens when I move this light further and further away. Conditions get brighter, less bright. Brighter, less bright. Pretty awesome. So there you have it. Oh, we're going to try to get it back to 0. 1. Yeah, 1 and 0. So what you have here is a demonstration of how well voltage divider circuits work. All you need is something that is basically dependent. Sorry, the best way I can put it, something whose resistance changes in line with the variable that you want to measure. So the resistance of this photodiode changes with the amount of light that is on it. You can change the photodiode to a light-dependent resistor. Straight up, completely different sensor, works on completely different principles. If I reopen this, the light's going to be off again. And watch that. Move the light away. It works. So as you can see, the sort of voltage divider circuit is a wonderful thing. You could have put a flex sensor, a temperature sensor, any type of sensor whose resistance changes depending on the value that it's sensing. It's going to work inside a voltage divider circuit. So I'll put a couple of links in the description of this video so you can read up on voltage dividers a little bit more. It is a concept that is absolutely central to all sensing, measurement, and electronics, so you should understand it well. So in the next tutorial, we are going to get back into our gravity shield and the gravity speaker, and we're going to look at trying to make a light theremin. See you then. Hello and welcome. In this tutorial, we are going to use the gravity speaker and the light sensor to make a light theremin. Now, we have a voltage divider set up there. We're going to use the DF-Robot light sensor. We're going to plug it in like this. So we're going to need to do some reshuffling on the circuit. We're going to need to pull out all these wires so we can house the gravity shield. Maybe, just maybe, I can zoom this in for you. Merge, so you can see it better. So we plunk this guy straight on. I just love the way this guy works. And we can use a PWM pin, perhaps, instead of having that LED blink, or maybe even together with that LED, we can find a, I think a 6 would be. So it's 0, 1, 2, 3. It already kind of works. 0, 1, 2, 3. 4, 5, 6. So the green would be there. Just to make sure that I got, this would have to be turned around. And there goes the sensor. I would need to also connect the 5V and the GND as well as that LED. So the 5V and the GND, actually, you can use this part of the shield. The GND is the first, so the GND can go back there. And the 5V can go there. And last but not least, we can get that 0, 1, 2, 3. So we need to also have a reading of this light sensor, and that's going to be interesting. Sorry, the LED, yeah, LED was at 3. And the reading was at a 0 right there. Sort of taking the reading from my hand here. But that guy should go in together with these. So right now when I re-upload the very last, and I'm going to go back into the view merge. So you see this, this code right here. This was the self-calibrating light sensor. That LED should go off. And the more we do this, the brighter the LED is going to get. Now, the reason I'm still having this LED is it gives me some visual indication of what is going on. What I'm going to do is I'm going to add the loudspeaker to the program and see if I can create a light theremin. So I'm going to call this int speaker, and we're going to have the speaker on at pin 6. We're going to need to set it as speaker is going to be an output. And while all this is happening, we're going to have to get rid of the serial printing. It's just going to be no room for that. We're going to have to get rid of these delays. And we're going to have to try to figure this out on our own. So the reading is initially 0. So I think that LED power should be the speaker power. So we can also analog write speaker, comma, LED power. And then we can make some delay. Maybe make a small delay. And then we analog write, oops, speaker to 0, and then we make that same delay. Speaker to 0. And then we make another delay of 1. So this should have the speaker go on at a sort of constant frequency, but the loudness is going to get higher as we shade that sensor, hopefully. We no longer have any serial, but watch. Pretty cool. And now let's see if we can change the frequency. See this delay? We can delay microseconds, and we can put in the value of the speaker there. Now, sorry, the value of the LED power. However, we may have to multiply that a little bit. delay microseconds. I'm going to put in LED power. And see how this works. I suspect it's going to be inaudible at first. So at low frequencies, it's not that cool. So what if we times that by 10? Times that by 10. What's the maximum LED power? About 500. So that'll make it about 5,000. Let's see how this works. So I'm just curious, if I used a light-dependent resistor instead of that photodiode, would we get a different result? Get in there, son. That's going to restart the program, hopefully. There is nothing. Okay, need to re-upload. Pretty cool. And I'm just curious if instead of microseconds, we delayed LED power. I almost feel like plugging out the loudspeaker. So if you just want to get some peace and quiet while working on something potentially annoying to your ears, you just upload a blank program. So what I want to do is I don't mind the speaker power being there. I don't mind what it is. But I do think that we can do something with the frequency. And I'm going to go int fric equals to 0. And I'm thinking that we can calculate frequency to be some variant of the LED power. So frequency, let's say it's LED power. I'm gonna try dividing it by 10, and then I'm going to so right now the frequencies have gotten, we don't have the extremely high frequencies anymore. There could be an issue with converting this, you know, the delay may have to be an integer, but it may also automatically convert to an integer. That's not too bad. And file new blank me. Okay. And just one last thing. If you wanted to shift the power to something consistent, let's say 800. would we get a sort of cleaner sound at least? That's what I'm curious about. Okay, that's all the experimentation I'm going to do. I suggest you make this your own, you build it, and that you have fun with it. Try both the LDR and the photodiode. They give slightly different effects. The photodiode is a lot more precise, is a lot more range, but somehow in this experiment, the LDR I think gave us a slightly smoother sound. So there you have it. See you in the next tutorial. Hello and welcome. In this tutorial, we're going to be looking at this little temperature sensor and getting a temperature reading in Celsius. Now, the sensor looks just like a standard transistor, but it's called LM35. And if I point the flat face towards you, what you're going to be seeing is the power pin, the 5V pin, is going to be on your left when you're looking at the flat face, and the G&D is going to be on the right. The middle pin right here, well, that is a signal, an analog signal that you can read. So you're going to get a value, just an analog reading, and to convert that to Celsius, you just need to do nothing other than multiply it by 5 divided by 10.24. So that is your conversion factor for the LM35. So let's get cracking. We're going to build this guy. Put the sensor in to the middle of the breadboard. So that pin there is going to be powered. That goes into 5V. And the leftmost one goes into GND. So do I have some blue cables? They'll go nicer. And there we go. Now the middle leg, plonk, goes into a 0. So back into our program. Arduino. There we go. So what we need to do is just essentially take an analog reading, have it displayed. I'm going to touch the sensor to see if it gets any warmer. And we are then going to try to have that multiplication factor. So int reading equals to 0. And we can pin mode a 0 to an input, and in the loop we can say reading equals to analog read a 0, and serial.print ln reading, and every time I write that I realized I have not initialized the serial.begin. Okay, so that ought to do it. Maybe delay of, I don't know, 50. We ought to be seeing some analog readings once I upload this. Good. Now, will it get higher when I touch it? Yes, it will. And we've gone across, and now it's 50, 51, 52. So that's great. That definitely works, and now you should see it fall back to 49, 48, so on. So right now, time to transfer that to degrees. So going back to the DF Robot page, I'll be sure to include the link. By the way, you can just Google it, DF Robot Beginner Kit Wiki. It's tutorial 7. So we are going to, that is the line. I don't like the way they declare any variables right inside the line here. So, but essentially you're multiplying by, we want to be multiplying by 5 over 10.24. So we can have something that's not an integer, maybe use a double, temp equals to 0, and then say temp equals to reading times 5 over 10. Yeah, that could work. And then we can serial print the temp just to see that it makes sense. Temp and serial dot print. Now what can we say here? Temperature in C. Let's have a look if this has worked out. Serial print line temp expected. So it's, as you can see, it's probably like 21 degrees, 21, 22 here. I'm wearing a hoodie, not a t-shirt. Yeah, that's perfect. 21.4. I mean, we could slow this down now to a 200, and we should be able to get rather convenient temperature readings. 21.48. Now, I'm going to put my hand closer and see if it gets to 22 without me touching it. Yeah, gets above 22. I'm gonna breathe on it. Rises a little. The most effective thing to do is actually just touch it. Your skin's probably in like 27, 28 degrees. The core of your body's at 36. But yeah, 24, 25. There you have it. A really easy to build, well-working temperature sensor that costs few cents. Okay, so see you in the next tutorial, and note that in the future we are going to be logging some of this data and trying to do some investigations with it. But perhaps for now you can also have a look inside the tools and the serial plotter. That's interesting. The serial plotter actually plots whatever you are printing to the serial. So since we are printing two different values, it is plotting a little bit of chaos. But if we simply got rid of that reading, we should be able to see sort of a moving line for the temperature. There you go, 21, and temperature staying somewhere around 21, and if we touch it, we should be able to make it go up to like 24 perhaps. There you go. And now if we let go, we should watch it come down. Just once more, that is in Tools Serial Plotter. Okay, second try it, goodbye. See you in the next tutorial. Hello and welcome. In this tutorial, we're going to create an RGB LED, this one, color mixer. And this is the schematics. Essentially, we're going to take these 3 PWM pins. We're going to actually just use standard digital writes for now and connect them to an RGB LED. And what today is inspired by is a documentary that I saw on BBC not so long ago about James Clerk Maxwell, the famous guy, I think he was a physicist, who discovered the equations of electromagnetism. But his first great invention was this color wheel. And this color wheel essentially spins. And if you can spin it fast enough, this portion of red, green, and blue becomes white. So I'm going to connect the RGB LED, and I'm going to try to figure out if I can make the colors blink red, green, blue, red, green, blue, red, green, blue, until they appear to be white. And then we're going to explore at which point exactly do our human eyes get fooled. So I'm going to zoom in on the circuit, and we're going to build this thing first. So we're going to use pins 3, 6, 3, 5, and 6. So 0, 1, 2, 3, 5, 6. The LED, this is the DF Robot RGB LED, there are two types. The longest leg is either going to go into the red or the blue. So it is cathode or anode first. So there's these two models. I know for a fact that the longest leg is going to go into the blue here. And dun, dun, dun. There it is. It's in. In fact, I'm thinking if I'm going to add buttons in the future or more devices at the start of the breadboard, I'm better off putting it out the back. So I'm going to put it all the way there. Come on. And I'll get these three. They're 220 resistors. That one was wrong, but I'll do it correctly for this one. And that guy's going to move over one and then up in there. So, I don't actually know which is red, which is green, which is blue, but this is something where I really recommend the experimental approach. It's only going to take us a minute to find out. So, if we jump into the code, merge. Where is my code? Right there. So let's just declare int LED red, and I'm gonna get them probably wrong. 3, then I'm gonna go green, blue, and I'm gonna go 5 and 6. But then we're just going to turn them on one by one, and we'll figure out which is which. So green, I'm gonna say 5, and blue, 1 second, and blue, I'm gonna say 6. Then I'm gonna pin mode all of those as output, pin mode, comma, output. Green, blue. So I'm just going to digital write LED red, comma, high, and I'm going to delay 1,000. So by the order in which they come on, I will know what is what. So the first pin 3, then 5, then 6 is going to come on. And if I have to change the colors up here, the names up there, I'm going to do so. LED, red, green, blue. So let's find out. The first color to come on is going to be pin 3. So pin 3 should be changed too. So it's going to be blue first. I really should have had them turn off. So this is going to be LED blue. I'm going to swap blue for red, although I could be wrong. And I'm going to turn the blue one on first. And What's your problem? So this time the blue one goes on first. Oh, and then if we get green, and finally red. I believe it's accurate. I believe it's accurate. Blue, it should be blue, green, red. So this should be green low. So if it's blue, green, red, we've got it right. Done. Beautiful. So we have our pin colors sorted. And now I want to make this. I want to make this sequence repeat sort of in a shrinking time. I guess I'm going to call int wait or pause. Pause. It's not a taken name, which is nice. Int pause. I'm just going to start with something fairly large. It's going to be 200. And just for my OCD sake, I'm going to start with the red. So I'm going to start with the red. LED red high. Then I'm going to delay whatever that pause is. Then I'm going to turn red low. And then I'm going to go to the next one. And red, green, perfect. This is going to be pause. So red on for this much time, then green on for this much time, and then finally blue. Blue on for that sort of pause time. So just to make sure it works, we should get red, green, blue, 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 red, green, blue. Just in case you're having a hard time seeing it, there it is in slow motion. Okay, so now what I want to do is shrink the pause. Pause equals to pause minus 1. And, well, if we're going to start at 500, we might as well shrink it by a little bit more. And what we want to do is say also if pause is less than, let's say if pause is less than 3, we're going to make pause equal to 2. Now you don't need the curly braces on the if it's only one single line. That's kind of one neat thing about Arduino. So typically I'd have curly braces around that if. But if I press Control T, no, that's just gonna neaten itself out like that. Okay, so I think this is worth trying. We're gonna start off with a ½ second pause. Red, green, blue. Red, green, blue, red, green, blue. And that pause is going to shrink. And what I am hoping to see is that eventually you won't be seeing red, green, blue. You will be seeing white. Let's find out. So I can't really tell if it's getting faster. Basically, the first half of the shrinking, by the time it gets to like 200, that's going to take the longest time. But we're going to wait it out. We're going to wait it out because I want to see. Yep, it is definitely going faster now. Red, green, blue. Red, green, blue. So in retrospect, I really should have started around 200. But nonetheless, if you get really close to it, you can see the actual tiny LED elements changing. And interestingly enough, the red is in the middle, so it's actually blue, red, green. If you look inside, like inside the LED. This just isn't. It's a lot less than half a second now. I'm just thinking, how many iterations will it take to get from 500, like 250 iterations? But yeah, it's getting there. The changes are getting harder and harder to notice. There you go, that's interesting. You can still see the changes, you can still see them, but we're getting there, we're getting there, we're getting there, we're getting there. The blue-green just happened so fast. And look at that. I'm beginning to see some white light. Wow. And that is white light. That is white light. And we can try to make this, I don't know, we can try to make it the sort of standard frequency. Even if we start at 100, you may still notice it, but I want to make it the standard frequency, which is something like 50 hertz, 50 blinks a second. So 50 blinks a second means that this delay here is 20. So we're going to go, so we're not going to see all three within 20. So I imagine the magic number is about 8 here, like a pause of 8. But I want to bring the pause down to 20. And I want to see if our eyes can catch this, or if we're going to see white. That, wow. There you have it. That's 50 hertz there. So for a 50th of a second, you see blue. Then for a 50th of a second, you'd see green. Then for a 50th of a second, you see red. And you can see that they're making white. They're essentially fooling your eyes, my eyes. And that's a very interesting property of human vision. Like, if we film that LED in slow motion, I guarantee you the LEDs actually go off. If not all the way, they go off 90% of the way. And we see white. We see white where there's actually just blue, green, red, blue, green, red, blue, green, red. That's pretty cool. Okay, so that is all for this tutorial. In the next one, we are going to be adding 3 potentiometers to mix these colors to make any color you can imagine. See you then. Hello and welcome. In this tutorial, we're going to create an RGB LED color mixer. Basically, that's a device that can create any color imaginable on that LED using these potentiometers as knobs, which can sort of turn the level of red, green, and blue. So we are going to accomplish that by using the PWM feature, so analog write on these pins on the RGB, and then controlling that analog write through 3 potentiometers. So I suppose we can look at that code that we previously had from the series of blinking red, green, blue, red, green, blue, red, green, blue, and see what we can do to just analog write a particular value onto some of these red, green, and blue aspects of that LED. So let's start by adding 3 inputs, because we're going to have them pin mode. We need 3 analog pins. I'm going to go from A345. So A3, comma, input. A3, A4, A5. Then we're going to have something like 3 values. So int red, or potentiometer for red. I think we can just say red level. Red level. I like it. Int red level. Red, blue, green. So right here where we have these delays can go away. Essentially, we're gonna get rid of all of this and make that into analog. Right. In fact, I would be faster retyping this in some respect. So first off, we, instead of high or low, we now have a range 0 to 255. What is interesting and strange is that analog read goes from 0 to 1023, whereas analog write goes from 0 to 255. So just for interest's sake, I'm going to try writing 100 to the green one. And there you have it. So we can now mix a bit of blue, 100. So that's green and blue. And now if we make it barely green, I can just put like 5, a tiny amount of green. Yeah, so it's mostly blue. So this stuff works. So what I would like to do right now is to set red, green, and blue levels. So we're going to read them off of the 3 pins, A3, A4, A5. So we can simply say red level equals to analog read A3, and then do the same for green and blue. So I don't even think I'm going to need to serial print here, but we're going to see. I think I will, though. I think I will, because I'll show you right now, because 255 has to be the limit, and I need to see green level. So we're going to write these 3 values on it, and then I'm going to control... I might just control green because it's the most visible of all the 3 colors. Our eyes are most sensitive to it. So I'm going to go serial.begin 9600. Very neat. And here we're going to go serial.print, and we're going to print red level. So we're going to go ahead and do this. And yeah, very interesting. I expected it to be higher. So we can now write in red level. Or wait, was I going to do green? Yeah. We can now write red, blue, red, RGB, green. Okay, for argument's sake, I'm just going to make the other 2 to 0, and I'm just going to control the green LED. So right now we should see a little bit of green, and we should know exactly how much green we are seeing. We are seeing about 70, 80 points. So our goal is going to be to make those values go from 0 to roughly 255. So I'm going to fix and set up that potentiometer now. Just for the green, we're going to check out that everything's okay. I think green is on... So green level is going to be A5. Rightio. So this, let me zoom you guys in. So this right here is going to be the green knob. So I'm going to connect that to A5. Oops, I think it should be there. And bang, see how much brighter? Inconsistent, max. So now I'm gonna put this potentiometer in. All I need is any one of the pins on the other side connected. And it looks like the potentiometer is down to 0. But look at this, check this out. So you see how it ends here? That means we got to 255 enough. So that's what we need to work on. So right now, that live reading is gonna be super useful. 514. 514. That 514 is a fair bit. 255. And does it go all the way to 0? Yeah. 0 to 514. 514 is more than 2 times 255. So now I'm going to try to make this dial, turn it from 0 to 255. And I'm going to write in green level equals to int green level over, and to get it, see, int turns it into an integer. To get it to 2.1, I believe right now when we put this guy in, we should top out at about 250, which will be perfect. Let's see it. 244. Yeah. Let's see if we can do a little bit better. Divided by 2.08. Yeah. 2.09. I don't know why I'm going to such detail. 245, it doesn't matter. 245 will do. And we can do the same for the other pins, because even though these potentiometers may just put those levels at slightly different values, we know the potentiometers are roughly the same. So we're going to basically... Oh, by the way, merge. Let me show you the code that I was working on, and let me show you what you were looking at, because this is what I did. I wrote int of green level divided by 2.09, and then we saw the values. And the values are right here. They are 245. So when I crank this to the max, it's 245, and when I drop it down, it goes to 0. And if you can look at the LED and the numbers, you're going to see that those numbers indicate the LED brightness, which basically gets our LED to the full range. And now I'm going to copy the same line of code, and I'm going to make it for the red, blue, red, blue. And I'm going to go back into the circuit and I'm going to build the other potentiometers. Should only take a minute, really. There we go. Let's see if we can keep the gap consistent. Dun, dun, dun. Get some of these. It doesn't really... We'll get them all into the bottom leg because that way we're turning the knob always in the same direction. 3 resistors going into this one. And now there we are. Can you see everything? Yes. So now that I have the circuit, I'm going to go back into the program and I'm going to upload this. And we're going to see if all the lights work well. So I'm going to crank everything down to 0. So I'm going to try the... Aha! Not complying. So this one isn't working, but that one. So, what's wrong? What's wrong? What's wrong? Aha, we are not writing the level here. We're not writing to the red level, and we're not writing the blue one to the blue level. Okay. So, let's check this out again. Ooh, looks like blue one's in the middle. Crank it all the way. Doesn't go off. Perfect. So we got blue good. We got red. Cranks all the way. And here we go. That's white. Turn them all on. Want to make a purple color? I guess we need to take out a bit of the green. Where's the green? Right there. There you go. You got purple. If it's too bright, you can turn these both down and make a more peaceful purple. I can turn these lights off so you can see the colors a bit nicer. 1 second. Whoosh. There you go. Purple. Bit of green already changes everything. I'm gonna turn everything to 0. We're back to white. I think the zeros are this way. Ooh. So the green seems to be cranked up. I'm having a hard time to get to 0. I disconnected that. There you go. Green. So let's see if I can make yellow. So that'll be green and red. There you have it. That's a yellow color. So I think I've done everything I planned to do with this tutorial. The code is really straightforward. The only new concept that we've already tackled a little bit is the PWM analog write, which allows us to write different levels of intensity to these LED pins. And if we were analog writing on the analog pins, these LEDs wouldn't work properly because PWM is a pulsing wave, and these LEDs just wouldn't work with a voltage that's like 1 volt. But if you give them a pulse of 5 volts that's on 1/5 of a time, it's the same amount of power as if you're giving them 1 volt. But that pulse is going to work, which is what makes PWM necessary. So that's all for this tutorial. See you guys in the next one. Bye bye. Hello and welcome. In this tutorial we are going to use this microphone module to detect a clap and turn on an LED. And we're going to play around seeing if we can maybe make it a double clap and so on, you know, getting a little bit more creative. And to do this, we're going to use this gravity shield that you see right now and the DF Robot sound sensor module. I don't know why they call it sound sensor, not microphone. It's a microphone. But it works really well. You're going to see the standard Arduino microphones that you get off of eBay have like a resolution of maybe ±5 on that analog port. This is ± hundreds, and it is virtually self-calibrated. So, all we need to do really is wire up an LED and plug this guy in. I'm just going to plug in into... should I zoom in? I should. So I'm going to plug this into A0. As you can see, the colors of the cable, they match. Blue goes into blue, red into red, black into black. The microphone, I don't know, I can just put it... I don't want to cause a short circuit anywhere, so I'm just going to put the microphone out there. I'm going to go around and just have the microphone stand right there. I now need one LED, which should be straightforward enough. Here's a cable. These are separated at, that should be 8. That can go into resistor. And that could go there. So the first goal we're going to have is just to print out a microphone reading. So we're going to start by, I suppose, declaring a microphone, creating a variable for a reading, and go on from there. So let me get you back into the code. Believe it or not, that this switch has made me have to redo multiple tutorials. So we're going to have an int for reading, and then that's going to initialize to 0. We're going to have an int for mic, and that's going to be a 5. And we can have an int for an LED. And I think we put that one into pin 8. So we can set the mic to input. We can set the MODE LED as output. Serial.begin is going to allow us to read the signal. Begin 9600. Okay, so here we are in the loop, and we can now set reading equals to analog read microphone. Great. Serial.print maybe ln reading. That was quick. Don't worry if you're not as fast, you will get there. Eventually, like, you know, once you get used to typing in all the brackets and the semicolons, things go quick. Okay, zoom in on it. As you can see, some numbers went up, and I can talk from here, and it's being detected. So now we got to make sure that we can turn on an LED with a clap. See, clap goes into the hundreds. So I suppose we can just say if reading. Now we are in Arduino, Sanyin. We're not in Python. We need to get brackets in. Reading is bigger than 100. If it's bigger than 100, then digital right LED high. And I think this if is gonna have to go into brackets because I'm gonna have to put on a delay. Keep it on for 2 seconds and then digital write low after the if statement. So this should just test whether, you know, the LED works, the clapping works. Then we're gonna do a Boolean to have the state of the LED change permanently. Okay. Yay! And let's see if I can get there by shouting. Turn on! I didn't have to shout. That's pretty good. I can do it quietly, nothing happens, but... On! On! And hitting the table. Man, that works too. Okay, so we're gonna need a Boolean. Boolean. I probably can get away with just saying bool. But Boolean, I'm gonna call it LED on. LED on, and we're gonna call that true. True should turn blue or orange or something like that. We can also use 1 and 0, and I guess I'm gonna use 1 because true didn't change colors. So now I can just have like 2 states. Instead of the if, I can just say if LED reading is greater than 100, then I can say LED on equals to, I think it's like an exclamation mark equals, like that. It means, or we can do it like that, equals to exclamation LED on. That makes true into false and false into true. It changes the state. So I can now say while LED on is 1, while it's 1, I can basically digital write D, comma, high. And you don't like me. Okay, try this again. So this way, clapping should like turn on the lights permanently. All right. I should have had a delay of 100. And I should serial print LED on. Hopefully, I'll be either getting a 1 or a 0 the whole time. Okay. While LED on equals to 1, it's going to stay high. But when LED on doesn't equal to 1, it should turn low. So something about this, let's just at least make sure that the LED on idea works. So if I'm going to upload this, I'm going to upload this and then at least see if the light comes off. So it's on by default. Should be. And then it's not printing it all the time, which means we are inside this loop. So it's an interesting situation, an opportunity to troubleshoot a little bit, so that if end statement ends there, the while statement ends there. And we are not doing the reading inside the while statement. So when the while statement is entered, no readings are done. And that is, it's not that the microphone didn't change, but it's that no readings were done in there. And I think right now, I believe that that statement was correct. So that's why nothing was happening. And this should work. I believe it's not just the reading, but after the reading, and that's the end of the while loop. So right now, the LED on can change inside the while loop. Perfect. So all I need to do now is, in this switch of the LED on, I need a little bit of a delay. Delay maybe half a second. So bum. Works 100% of the time. Okay, I think we're about 11 minutes, nearly 12. And I suspect that I'm gonna have to use nested if statements and maybe get rid of the booleans if we're gonna succeed in that double clap switch. So I'm gonna leave that to the next tutorial. So I'll see you then. Bye bye. Hello and welcome. In this tutorial, we are going to upgrade our clap switch program to only work with a double clap. At this moment, this clap switch, well, let me just show you. On, off, isn't responding only to claps. And I'm wondering if we can make this code work so that when I do this, the state of the light is going to change. And it won't change when I talk normally. So let's see what we can do. First things first, I'm looking at this code. And on a second look, I think that this while loop here is entirely redundant. This is how you would program inside Python, inside C, inside any other programming language, that your program doesn't happen inside a loop already. We are inside a loop. This loop is running forever. We could have just done a simple if-else statement instead of this whole while thing. So if we just did if LED on equals to 1, we're going to digital write LED high, and else we're going to write low. That's all it takes. Control T. And I believe that once I upload this, it still works. Excellent. So, time to brainstorm how exactly we can get this thing to work on a clap switch. Before I get started with that, do you see this if else? The else only refers to this if. If and else, you can always think of them as a package. If else. So this else has got nothing to do with this if here. So that said, let's get started. We are having this case here. If reading is bigger than 100, change the state. Well, what we're going to do instead is if reading is bigger than 100, we're going to delay we're going to make a delay. We're going to make a delay, I don't know. I'm going to guess half a second. And then after half a second, if the reading is again greater than 100, we're going to take another reading. And then we're going to change the state. So LED on equals to not LED on. So this code is problematic, and it's problematic entirely because right here, this if here is inside a forever loop. So it checks thousands and thousands of times per second, whereas this this reading here, in fact, that should have been right before the if. This reading here is checked once. So checked thousands of times, checked once. But I'm pretty sure that we'll still be able to make this work. At least, you know, like a quarter of the time. So I'm going to upload it and see what happens. Okay, that's way worse than a quarter of the time. Let's try it again. Okay, so that's an applause switch. That's pretty bad. So how do we fix this? Well, the answer is pretty simple. We just make sure we don't take one reading, we take, say, 1,000. So right here, we can do a for loop. For int I equals to 0. Okay. I is less than 1,000. And I plus plus. Open here. Well, I guess we can close that if there. So this loop is within that control T. So there we have it. That reading is inside this loop. We can take 1,000 readings, so we can delay 1 millisecond here. And once we get out, once the state changes, we can get out of the loop. Break. So let's try that out. Wow. And I'm going to talk normally right now. I'm going to do it for a minute, and I'm just going to watch that LED and see if it ever goes off. And it really looks like it will not. It won't, it won't, it won't. And we have solved our problem pretty well, pretty neatly. Oops. So you have to let a couple of seconds in between. I honestly think that is the best clap switch I have seen yet. It is literally 100% reliable. I'm very happy with this. You guys go ahead, build this, and maybe try it out. Try it out with an RGB LED, put in a motor or a servo or something else that's pretty exciting. Okay, I will see you in the next tutorial where we try to build a circuit that has essentially a response to the intensity of the sound, much like those sort of music bars that we have on stereos. See you then. Hello and welcome. As you can see in this tutorial, we have 6 LEDs connected to pins 1, 2, 3, 4, 5, and 6. And what you're seeing here is the program that we're about to build. Hello, this is a sound sensor, in a way. The louder I get, the more it reaches the red bars. And obviously, the closer I am to the microphone when I'm talking, the easier that happens. And I can also smack the table, which I'm not really going to make a habit out of, and activate those sound bars. I actually twisted the tripod a little bit. There you go. We're back. So our goal is to write a program that does what you see out there. And I'm going to try to do it in a very, very elegant way. So let's get into the Arduino. So first up, what we want to do is declare 6 pins as input. And I think I can get this thing done in like 2 lines of code, plus a curly brace. So we have a for loop for int I, and remember our first pin is pin 1. So we can say int I equals 1, and then I is less than 7, which is going to go up to 6. Or if you want to do it this way, less equal than 6, then I is also going to count 6. And then I plus plus. And inside this for loop, we simply pin mode. Dun, dun, dun. So I, it's going to be 1, output 2, output 3, output, etc., etc. Output. And then we can kind of copy this. And in here, just to show you how it all works, I, high, and obviously this is going to need to be digital right. Okay, let's have a look. Oh, curly braces, curly braces. So that should turn all of them on. Happiness. There we go. All the pins are on. And it's actually, you see, LEDs have particular viewing angles. And I can tell you that the green ones are as bright as the red ones. But clearly, if you face the camera at a certain angle, they appear brighter, which is interesting. So right now, what I want to do is print print the sound level, and then try to introduce the sound level into the loop and into which pins turn on. So let's have a look at that. Perhaps before we start, I'll just give you a quick zoom in on the board in case you're wondering. So there you can see the 6 pins 1, 2, 3, 4, 5, 6 connected to the 6 LEDs and the microphone connected to A5. Okay. Merge back in. So let's get started. So our first goal is to just get some readings. So we're going to need to have a microphone int, I guess, mic equals to A. So that, you know, like a letter A being declared as an integer wouldn't work in any other program, but Arduino is designed to accommodate that. So we can have a reading, which is going to be, it's going up to 1024, so why not? Reading equals to 0 initially, and let's leave it at that. So we need to serial.begin 9600, take a printed line, and pin mode mic is an input. Okay, so inside our loop, after we turn all the pins on, I think it's better that if we get that done on the top actually, we can say reading equals to analog read mic, and then we can serial.print ln reading, and delay 200. So here we go. We're going to print 5 readings per second. Semicolons. Come on. All right. Dun, dun, dun. 0, 30, 20. Okay. As you can see, most readings are 0. And I'm just gonna do something like shout to have a look at what is a high reading. Loud! 57. Okay. Just in case, we're going to do a little experiment. And we're going to say if reading is more than 10, then we're going to serial.print ln reading. So get rid of that delay, get rid of this. So we're going to print all the readings that are higher than 10, and this way we're going to know objectively like what is a high reading. And I want to know, because we use like 100 as a threshold for the clap, I just want to know for voice, because we're not going to be clapping, what is really loud. So Control T to make sure everything is indented properly. When you have an if statement, you don't have to do curly braces if you're only doing one line that depends on that if. Okay, so big moment of truth. Okay, this is fairly quiet. We've gone up to 40 something. 35. Okay. Now I'm going to go loud. Loud! Okay, get rid of the auto scroll and have a look. Any 3-digit numbers. Oh! Ooh. Wow, okay. So it does get into the high 100s. So if I'm thinking if I have 6 lights, maybe 120 should spell 6 lights. So we're going to need to figure out how to have like a level. And a level is going to indicate how many lights are turned on. So this is going to be a variable called level. And we're going to have an int level. And I'm just thinking, if we say, ooh, turn on pins 1 to 20, that won't matter. So let's think about how we want to specify our level. So we want to, level is how many LEDs we're going to turn on. So we want to turn on all 6 when the sound is at 120. I think that's kind of a reasonable number. So level equals 0. So we can say here level equals to we were going to go reading over 20. And we're going to have to convert that to integer because obviously we're going to get a non-integer number. So now we're going to turn on as many lights. And then we're going to turn them off. So we're going to need a delay in here. Maybe 100. Let's see. If reading is over 20, so int, I don't really think we're going to need this at all. So it's going to turn, but the point is it's going to detect the first reading. So it could still work reasonably well. I think we're going to need a tiny delay. I think we're going to need a delay of like 50. And then we're going to turn them all off after this delay. Okay. So let's try this out. Hello. Hi, where is the mic? This is not working too well. It kind of, I think we're taking a, I think this delay of 50 is kind of messing us up. So we're gonna, what if we were to leave that, and with each one of these coming on, we can have a delay. And maybe it'll be a small delay, maybe 20, something like that. Let's see if that's gonna work. Hi, yeah, this is actually really good. I really like it. Go, 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 go. So this level can be, you know, if this is not sensitive enough, we can, you know, increase the levels, and I can actually bring up a song on like YouTube or something. I think there's a present sensation in the meme hemisphere is a one called "A Man's Not Hot." A man is not hot. All right.
You know what's happening? You know what I'm saying? Are you ready for this, G, yeah? Frisbee. Trap on the road. Moving that cornflakes. Rice crispy. All time I dealt Whitney. On the road doing 10 toes. Lava toes. You man thought I froze. I see a bang out in a pose. If she's not on it, I'll ghost. Ha! Look at your nose.
It's pretty cool. Okay. So there you have it. That is a very neat, very tight, very elegant sound reacting circuit. And I think you may have to make some adjustments. I think when I changed that to 15, it worked much nicer. And again, depending on what you wanted to react to. I think mine was perfect for music, not quite perfect for normal sound and audio. One advice, one challenge I want to leave you with, and I may even put it here as a comment. Can you make lights turn off one by one? That will be a little task. You can make it count backwards and then have these lights turn off one by one and maybe have a delay of 20. So instead of them coming on slowly, they can also go off slowly. That is the only improvement I can think of right now, and I would like you guys to try to do it. Excellent. That's all for this one. See you guys in the next tutorial. Hello and welcome. This is an introduction to Module 4, Digital Circuits. Perhaps it should be called Advanced Digital Circuits because this is where the fancy stuff begins to happen. So, we first create a button-controlled buzzer. So we start messing around with Arduino tone functions, which essentially generate sounds of different frequencies. We do this both with a buzzer and a loudspeaker. The loudspeaker is actually really good. Then we take that into two applications. We create a piano out of it, as well as a sound effects generator, which gets really interesting when we actually create what a Fibonacci sequence would sound like if the frequencies were shifting in a sort of Fibonacci order. After that, we create a 8-segment display. The if robot calls it 8-segment. I've more used to it being called 7-segment. And we then use that circuit, which basically displays a number from 0 to 9, to create a game where you guess a number. And the serial monitor tells you if your guess is correct. This perhaps brings up some issues with the sequences not being truly random, which is an issue with Arduino. But we solve that in a little separate tutorial, which uses a function that Arduino created specifically for this type of problem. So after that, we have a reaction time measuring circuit, which is actually a really simple circuit with nothing other than a light and a button input. But we get really fancy with that. So we look at different ways of displaying the results. We look at ways at storing results and in arrays. We calculate averages. And so I think this is the first time we really get into data and how Arduino can be used to either store it or manipulate it. So next one is a memory game circuit. I have fixed the typo, but it's still there. Memory game circuit has 4 lights that come on in kind of random sequences, and you win the memory game if you repeat the sequence. Of course, you can make the game as hard as possible and virtually impossible to win, but nonetheless, we create that premise, and it's quite interesting. Okay. That's all for the introductions. See you in there. Hello and welcome. In this tutorial, we are going to use a push button to turn on and off this buzzer. Now, this buzzer works on the same principle as a speaker. In other words, it's not always on. If you connect it to plus and minus, you'll hear nothing. You have to oscillate the input, so to speak. You have to turn the plus pin on and off, 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 and then the buzzer is going to make sounds. And you have to do this at a reasonably high speed. So let's hook in the circuit. We'll start with the button, then add the buzzer, and then we're going to play with some code. So button goes in across the channel right here. We can connect that to the positive, and we can connect that to minus. We can then take a cable from the button into pin, I don't know, 0, 1, 2, 3. Dun, 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 dun. Next up, the loudspeaker. Now, we just gotta sort of watch out where we put it. 6 and 7, rows 6 and 7. The minus is going to go to 6. Dun, 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 dun. I think I could be 1 row off, but I think this is the minus. I'll put it there. Let me actually zoom in on this whole thing, which I forgot. So the wires that are out here, I'll just try to sort of fold and put into these pins so you guys can see a bit better. And then we also need to get the plus into pin, I guess we can use like 8. Nice and convenient, easy to locate. So let me place that guy down as well. Yeah, fairly neat. Now we just gotta hope it works. Let's pull up Arduino. So we have button in pin 3, code pre-written, button set to input, and wow, we need to merge this. Sorry guys. As I said, button into pin 3, button here set as input, code already pre-written, basically that says, oh, if digital read button is high, we do whatever is there. I think the code needs another bracket, closed bracket that is, to close the loop. We can click tick to make sure everything works. So we should be good to go to add a little buzzer. Int buzzer, we'll put it into pin 8. We're gonna go pin mode, buzzer, it's going to be an output. And here we can oscillate the pins. So digital write, buzzer high, delay 100. we're gonna, with high and low, and a delay of 100, that means that it takes 200 per wave. So we're gonna have 5 beeps per second. So buzzer is gonna be low here, and we're gonna delay 100. And now's the moment of truth. Compiles, certainly does. Upload. Oh, and nothing happens. So my guess is that these are, because I can't see where the buzzer pins are, I think these are both one up too high. So lovely. That works. And I think you can barely hear that, but that's 5 per second. Let's do 500 per second. Pretty good. So let's try to do 5,000. Now this is, I'm just going to use something called delay microseconds. And microseconds is sort of a very buggy function that there's many workarounds, because in order to do it, you virtually have to interrupt other things that Arduino is doing. I mean, the Arduino operates on a clock speed of 16 megahertz? So yeah, 16 million times a second. So if you're dealing in terms of millionths of a second, you are literally sort of messing with internal workings. And interestingly, it works reasonably well when you do something like 100, but if you were to do tens of thousands of microseconds, you'd run into some sort of patchy territory. But let's try this out. This should be much louder. So on the fun scale, which means on the scale of sort of human, on the scale of what human ears are trained to hear, this is sort of the peak frequency. This is the frequency at which babies cry and scream. It's kind of annoying too. So there is, of course, as I said, if we don't want to mess too much with microseconds, we can write a function that does something like this. Arduino has created tones. So we can create tone. I think you go pin name, buzzer, and then you do frequency, 5,000. So unfortunately, if I run this, once I press the button, it's not going quiet at all until I create this thing called no tone. There is that same frequency. Interesting. And let's create a no tone. I think it's like that. Buzzer. Lovely. I don't quite understand that. I think after no tone, when you're calling tone thousands of times, I don't know. Let's put a small delay, like delay 10 here, and see if that makes a difference. Certainly does. And Control Z. Maybe a bigger delay would make it a clearer sound. So clearly this delay has an impact. I'm going to run with 100 because you really don't notice. Even 0.2 of a second you wouldn't notice. After you lift the button it would stop working. So I find that interesting, that the tone and the no tone, once you introduce the no tone, you're calling the tone like, you know, millions of times, sort of makes the tone interrupted in some way. But there you go, this works reasonably well. And we can do something really cool like int frequency. And we can start off at 10. And watch this. We're gonna actually run it at frequency. And then, instead of having the no tone, we're gonna have no tone. We're gonna run it by default. And when the button is pressed, we're gonna go frequency equals to frequency plus 1. And how much can we add per second? We can add maybe 100 per second. We can put a delay of 10. So this should, in theory, keep the tone always on. But the longer we hold the button, the higher the frequency gets. And since there's no upper limit to frequency, we don't have to, you know, we can go from barely audible to super audible to barely audible again. Basically from out of the range low to out of the range high. So let's try this program. That's pretty mad. Okay. We need to plug something out. Okay. I think we can try this, and we can maybe have a serial.begin. And we can listen to various different frequencies. Personally, I think the frequency of 10, for some reason, isn't accurately represented, but the rest pretty much seems to be. So I can actually, when I'm pushing the button, so we're going to increase the frequency by 10. I'm going to delay this by 100. And then I'm going to serial.print. ln, we're going to print the frequency. And that everything is there. Okay. So this time around, when we plug back in, we should be able to see a live display of frequencies. Okay, get ready. We're gonna have, and that's that tone there. I'm not sure if 10 hertz sounds like that. Maybe it does, but let's have some fun with this. 60. Yeah, that's more like 60. So initially, 80. 100, 200, 300, 430, 610. So 5,000 should be like the peak. It's gonna take us a while to get to 5,000. Oh yeah. Okay, this is like hurting my head a little bit. Whew. Okay, in the next tutorial, I'm just gonna have some fun and do that with a proper loudspeaker. So we're gonna run the same code on this gravity loudspeaker by DF Robot, and we are gonna see if there's much of a difference between this little buzzer and a proper loudspeaker. But that in principle is a frequency generator. And based on the code there, we can set up 4 buttons in the future and have ourselves a piano with, say, 4 keys that play 4 different frequencies. Excellent. See you in the next tutorial. Hello and welcome. In this tutorial, we're going to rerun this frequency generator button tester program with these 2 fellas. So this is the gravity shield, which allows various gravity components to just plug and play, essentially. So this DF Robot gravity shield is going to go straight onto Arduino, and this DF Robot speaker is going to go onto the gravity shield. So as you can see, the speaker is going to connect on this side. The pins are color coded and numbered, which makes it really easy to plug in. And I'm just gonna, in fact, I'll do it on the board over here. So I'm gonna put this shield in. Should just go straight in, no dramas. And as you can see, green turned towards green. I'm going to plug this into number 8. And then I'm gonna proceed to connect the button. Now, I guess I can put the speaker up on top like this. Dun, 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 dun. Doo, doo. Or I can put it over there, I guess. So long as it's kind of out of the way. So all I need to do is reconnect 5V GND and the pin 8. No, I don't need pin 8. This guy can go out. So with the shield, you're going to need some female to male pins, which are in the DF Robot kit. Dun, dun, dun. So we need a red and a black one. Should only take a second. Black, red. Here we go. That's a 3.3. So, funnily enough, all of these are 5V pins, and all of these are also 5V pins. So, lots of choice. I'm just going to chuck that over there. And that's over there. Okay. Then we need a pin 4. 0 TXRX 0 1 2 3. It was actually pin 3 where the button was. Okay. I know that looks messy on the screen, but this goes into pin 3. Actually, the D, the green, should go into the green part of pin 3. 0, 1, 2, 3. Right there. These two, 5E, G, and D. All of these pins on here are actually GND 5E and analog. So we're going to plug this into the GND and 5E of just, I guess, whatever that is, A5. And I think we should be good to go. I'm going to upload this and we should hear a 10 hertz tone. And now we're going to increase the frequencies. So this is more like it, actually. I'm going to So the very first tone it makes is not actually 10 hertz, but this is definitely 20, 40. Oh man. Okay. If you want to annoy people, you need to get this and play with it. I can't even go any higher, but there you have it. The Grove loudspeaker, Gravity loudspeaker works way better. Way better. It's way louder and it's killing me. Ugh. Finally some normal sound. Okay. I will see you guys in the next tutorial where we take this and make it into a piano. Hello and welcome. In this tutorial we're going to build a piano circuit, and to do this we're going to use this DF Robot Gravity speaker module. And we're going to combine that with 4 push buttons, each of which is going to create a different sound frequency. So I guess we can get started into creating the 4 push buttons. Now let me zoom you guys in on the breadboard, and I can place these guys right across the channel. I guess we can skip one. Close, tight backing is good. So there we go. So from this gravity expansion shield, as I said, there are basically, I don't know, 25 plus GNDs and 5Es. So every black pin is a GND, every red one is 5V. I could as well have, connected that to here or anywhere else for that matter. So now that we've got these buttons in, I guess we can put a resistor to tie each of them to earth so that they're all GND and or 0 by default. I got 1, 2, 3. A bunch of resistors lying about. I'm not even looking at whether these are like, I think I've been using the 10K ones and the 220 ohm, and it doesn't really matter because either one will do. So the 4 buttons have been earthed. Now I gotta get the 5V into them. On reflection, when you do this, you can just do the earth followed by 5V, because I gotta get in between there and put these in. As usual, I always note that you can indeed use those much longer jumper wires. They're a lot easier, but this is neater, and we're going for neatness here. Oops, nope, that guy is going one away. And last but not least, small camera adjustment. Okay, there we have it. Now what pins do we have on this drawing? I'll show you. We've decided to go with 3, 5, 7, 9. and then we're gonna put the speaker in 12. Okay, 3, 5, 7, 9. There's a bunch of these. Okay, 0, 1, 2, 3. There we go. 3. So skip 1 should get you to 5. Here are the green ones now. Seven, 8. That would be 7. That would be 9. Okay. So then that's the 9. So, since you know where these pins are, I can just sort of put them at the extremities here. Yeah, that'll do. That'll do. You can see the buttons clearly. Okay, so now we put in the speaker, and then we're going to test this for one button, and then we're going to program the rest. So the speaker goes into 12, which is simply the second last. Should be very easy to locate. And we can place the speaker on the breadboard over there. Finally, we get to do some coding. So, Arduino, merge, here we go. So we're gonna have a buzzer, and then buzzer this time is on 12, and we're going to have 4 different piano keys. So I don't know, we can call them key 1, key 2, key 3. Key 1 equals to 3. Two, 3, 4, and this button here is obviously going to be key 1. And we're going to have some code for key 1. If key 1 is an input, then so are the others. 2, 3, 4. Then buzzer is going to be the output. Pin mode, buzzer, output. There we go. I think we can try this out. So we're going to have the tone, no tone. So outside of the if statements, we're going to call this no tone on the buzzer. And in here, we're going to have tone or a little tone, tone, buzzer, and I don't know, I'm just going to do like 200. We're going to start off with that being our first frequency. And we're going to see what happens. What delay did we use? Delay 100. Okay. Compiles, no drama. And buzzer 12, button 3. Let's have a look if this guy is actually connected. 0, 1, 2, 3. There. That's the 5 volts. That's the 5 volts. Okay. So what we're gonna do here, I'm gonna call it pin mode. So 13 would not be visible actually because we're using the shield. I'm just wondering, how is it that we can test? First of all, that the buzzer works. I guess we can put some tone in by default, so at least we know the problem will be with the button. Okay. No tone. Buzzer. Okay. So, stage 1 of our troubleshooting, successful. We know that the issue is definitely with the buttons. So, next thing I'm going to check is the wiring of that first button. I'm going to have a look at the positives and negatives, and I'm just going to try to maybe put these guys in a different position, see if that makes... Very interesting. So I just connected the earth and the 5V the wrong way, and that happened. So that's number one, but number two should do nothing. Right. So I feel like the 5V right here isn't transferring, so that could be the issue. Try a different button. There it is. These buttons can be temperamental, but that works. So now you can copy this code and do different frequencies for different keys. Key 1, 2, 3, 4, and go 200. Let's see. Let's go 200 to 600. We go 400 up each time. 600 to 1,000. This is just one way you can tune it. I decided to crank that up to 2,000. See how that works. So that's really good. None of them have gone off by accident. Oh. All the keys are number 3. So 3, 5, 7, 9. I think we have it. And you can use 2 at a time. There you have it. That is your basic digital piano. In the next tutorial, we are gonna pick up from this very setup and see if we can create other interesting sound effects. See you then. Hello and welcome. This is going to be the sound effects circuit. So right now we have the piano circuit. Dun, 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 dun. And, sorry, I had to play that. The goal is going to be to write 4 functions to create 4 different sound effects. In fact, I think I'm going to write 3 functions and I'll leave the last one to you guys to see what you can come up with. So, we're going to introduce, in effect, in the course for the first time, 2 new concepts. The first of which is a loop, the second of which is a function. So, first thing I'm gonna do is I'm gonna try to create a bit of like a gun Formula 1 passing by type of sound effect. And I'm gonna do that on key 1. In fact, I'll just write the loop here. So what I'm gonna do is create a so it's a for loop. So in Arduino, you have to declare the looping variable int I equals to 0. This is called the initial condition. So there's a counter, the counter is I, and we start counting from 0. Then you say we count until, well, I is less than, say, 100. That's sort of the upper limit of the count. And last, but you say I equals to I plus 1. You can also say I plus plus. It means I plus plus, or I equals I plus 1, just means that you're counting by 1. So you're going to count from 0, 1, 2, 3, 4, 5, 6, 7, 8. So, in effect, once I've done this, what's in between these 2 curly braces is going to get repeated 100 times. So if I just did the, you know, your classic digital writes buzzer high delay, and we're just going to go delay 1. So if I did that 100 times, I would press the first button. It would make this sound for 100 times. Expected semicolon. Alright, so I mean, I don't know how long will this last. 100 times. And watch this. If I said do this 1,000 times, I'm going to press the key and it's going to keep going after I let go. So that's a loop. So right there is these 4 lines repeat 1,000 times. So instead of delaying by 1, you can delay by I. And you can check this out. It's going to be interesting. It's going to go, I don't know, it's going to make... And given that it's going to go for 1,000, this break is going to be 1,000 in the end. So this is pretty boring. If we made it 500, maybe we'll hear the end of it. But probably not. It'll be the same. And eventually... So what we want to do is try microseconds. So let's see. 500 microseconds. That's... That'll probably be too fast, way too fast. That's actually pretty good. Let's see, maybe 800. I'm liking it. So there you have it. This is a for loop. This repeats 800 times, but this I is also a counter. It starts off at 0, then it's 1, then 2, then 3, then 4, and so on and so on and so on and so on. So you can take this code that we created and you can put it in a function. So I'm going to show you how to do that. We're going to create a function. We're going to call it void because we're going to cover this in the future. Functions can return a value or not. So a function can be just a bunch of lines of code which can be repeated every time you write sort of the word of the function. The functions can also have inputs. So to see this upper limit here, that could be the input of a function. So we can go, I guess, space guns. Well, space gun. So, and then int, I don't know what we're going to call this, maximum. So maximum is going to be sort of the I limit. So see these two curly braces, they define where the function begins and ends. And what we're going to put in here, I'm just going to cut this whole for loop. No, cut. Paste. And that's going to be maximum. So check this out. Instead of calling, instead of at this point having all this code, we can just say space gun, and remember how we had 800? We can go a really brief one again. We can go space gun 500. That's a really brief one. And with just one click, you can have a 5,000, which is going to be a much lengthier sort of So I would advise not to go over 1,000 because that could be the bug with Arduino, that microseconds serve their purpose, i.e., see when you get over 1,000 microseconds, you really should be using milliseconds, you should be using delay. And when you're having delay microseconds over 1,000, there could be a few bugs. I think that just lasted longer than it should have. Let's try 1,000 and see how that goes. That was a lot of fun. That was a lot of fun. Okay, so we've already used the random function below with lights. And now I'm going to play around and see if we can use the random function with, you know, sound and tone generation. So let's think about what we can do. I mean, what we're doing currently is we're just doing tone, buzzer. I guess we can just go tone, random, and I don't know, 100, comma, 1,000. Okay, so random, brackets closed. I think that's gonna work. So I think, what do we got? We did it for tone 3 for whatever reason, not tone 2. Sorry, button 3. But have a listen to this. Oh, you silly man. You meant to specify, and this will allow me to correct it anyway and put it in the in number 2. Number 3 can go away. You meant to say buzzer there. So Control C, Control V. That's going to be, the random is going to be the actual frequency, but the pin isn't random. The pin is the buzzer. And let's see. And you can make it, I'm really curious if it was like 50 to 300. Would that be too brief? So you can sort of specify the upper and the lower limits. Oops. I like the other one better. So let's have a think about how we can turn this into a function. So let me cut this, and let's create another function. This guy here is done, so we're gonna call, and we can just copy that. Dun dun dun. Void. What are we gonna call it? Rand sound. Dun dun dun. We can have a sort of maximum input. We can. Oh no, we got rid of that. So I gotta remember now what we did. Tone, buzzer, comma, random. And this is where the fun is. We can say random maximum. That can be the lower limit, and the upper limit can be 10 times maximum. So, delay 100. We can even delay maximum. I mean, that's gonna be. So we can now try calling rand sound on key 2 for different values. Oops, Control Z, rand sound. Let's call it for 100. And then we're going to call it for 1,000. We're going to see what's the difference in how that sounds like. Why, man? Aha. I am bad with the semicolons. If the software didn't have proper debuggers, I'd be in big trouble. Alright. So, here we go. This is the space shooter, and this was the random one. And you can now try, instead of 100, you can try and make it 500, which is going to, at least I think, sound completely different, because it's going to be in half-second intervals. And we could have tried 50. Which is going to be much faster. Oops. See, that's a lot of fun. Okay, so I'm going to finish off with something really, really, really cool. Okay, I want to do the Fibonacci sequence, which is not going to be so easy. So how I'm going to do the Fibonacci is we're going to go, just like Fibonacci sequence is, well, Fibonacci sequence is like a sequence that starts with 1, 1, and 1 plus 1 is 2. So that's the third one, and then it adds the previous 2. 2 plus 1 is 3, so that's the next segment. Then 3 plus 2 is 5. And then 5 plus 3 is 8, and so on. You're going to see it because I'm going to print it. So I'm going to kick in the setup, serial.print ln, just to know that I'm doing the, not print ln, serial.begin, just to know that I'm generating the Fibonacci sequence correctly. So my first goal is going to be to print out the Fibonacci sequence and then to use that inside delays. So what are we going to do? Void Fibonacci. And then I guess we can have int maximum again, because we're going to generate it up to a number. Or we're going to generate a certain number of Fibonacci numbers. Okay. So first we're gonna need to like start. I think we need to generate some Fibonacci members. And I'm using longs instead of ints because ints end up at like 36,000. And I think there's a real possibility I could have a number bigger than 36,000. So long, I'm gonna call it, I'm just gonna start the sequence. Long fib equals to 1, and then long fib 1 equals to 1. Long fib 2 equals to 2. No spaces in variable names, semicolons at the end of everything. Okay. So then I'm gonna serial print. Watch this. Serial dot print ln fib. So this is the first member. But then I'm gonna define the next member. See, it's gonna be fib, and fib equals to fib 1 plus fib 2. So the next, so it's gonna be 1, 1. So actually, no, I'm gonna start with 1, and then I'm gonna have the next one be 3. So let's see if it goes from 1 to 3 to 5. Because even if I don't have the 1, 1 at the beginning, I don't think that's a big deal. Let me have a think about it. So I'm gonna go fib 1 equals to fib 2. And fib 2, well, equals to fib. I know this whole thing seems a little bit convoluted, but watch. We're gonna print it and we're gonna call it, and the number of times we're gonna do this is going to be bounded by the maximum. So all I gotta do is take all of this and put it in a loop that repeats a maximum number of times. So for int I equals to 0, tuck, I is less than maximum, tuck, I plus plus, close bracket, open bracket. Okay. So here comes the test. There's no tone generated. However, Fibonacci 100, let's see if we get 100 Fibonacci numbers. Mind you, we are going to be missing 1 instead of starting at 113. But given that the delays are gonna... Yeah, I don't know that it's gonna matter much. What's your problem? There you go. I think that needs to be there. What? Okay, I won the world championship in the forgetting of semicolons. And key 3. Oh! But that should have made it into the next one. I think these need to be created outside the loop. That was my problem. See, when the loop begins, these should already be created. Let's try that again. And press key 3. As predicted, it starts 1, 3, 5, 8, 13, 21, 34, 55, 89. Okay. 144. Beautiful. That is the Fibonacci sequence. 144, 233, 377. Yes. So, other than missing the one on top, which I'm not really going to worry about fixing, we have the Fibonacci sequence. And from now on, all we need to do is introduce a tone with a delay fib, and we should be done. So, tone, buzzer, comma, fib, delay, I don't know, we're gonna go for 200. And moment of truth, turn that on. So the maximum is way too big. We can just do the first 20 numbers. That's pretty cool. Random, space, random, and Fibonacci. And Fibonacci is quite melodic too. Okay, so we've been at this for nearly 22 minutes. It's the longest tutorial yet. I hope you've had fun with it, and I challenge you to do something of your own for that last remaining key, which doesn't do anything interesting yet. See you in the next tutorial. Hello and welcome! In this tutorial, we are going to set up and use an 8-segment display. Now, an 8-segment display is on one hand a very simple piece of equipment. There's just 8 LEDs that you wire up to 8 pins on the Arduino. On another hand, it is quite complex in terms of, there's a lot of these wires, and no matter how many times I recorded this video, I couldn't make it so that it is really clear where these resistors go and how these wires are wired. So you guys will have to make do with the schematic. But in the schematic, rest assured, all that happens is 8 pins go into 8 ports onto the 8-segment display. Now, in the middle right here is a 5 volt. So the way the circuit is set up is when any digital pin here is low, when the pin is low, then the circuit is made from the 5V to the low pin. So you actually need to turn these pins low to light up the lights. Now, let's get into the circuit, and the first thing we're going to try to do is turn on all of the lights. So how do we do that? Well, I guess we need to set up all the pins as outputs. Pin mode 2, output. And we are I think I did one too many. 3, 4, 5, 6, 7, 8, 9. Perfect. So now they're all outputs. And in order to write, to turn them all on, you can digital write. Dun, dun, dun. To high. And in this case, I'm just going to go, instead of high and low, instead of high, I'll put 1. And instead of low, I will put 0. It's just a bit easier. And you will see that we're actually going to use a array list to essentially write 0s and 1s into the digital write statements. So I'm going to turn them all low from 2 to 9. 9, 8, 7, 6, 2, 3, 4, 5, 6, 7, 8, 9. I think I got one too many this time. 2, 3, 4, 5, 6, 7, 8, 9. Yeah. So right now, I believe I'm going to turn on all the segments. And I think we want to get rid of the dot. So let's see if the dot is the last one. Yep. And I'm just curious, what's the second last one? That's not a real number, but that's cool. Okay, so we can essentially remove pin 9. We don't really need it. It's just that dot on the end. We're not going to use it. So what I would like to do is essentially turn this here into a loop, and a loop that reads from a list. Essentially, we got a list of 8 zeros. So I can write 0, and an array list is created like 2 square brackets equals 2, and then you go 2 curly brackets, and then you have 8 numbers. You can have as many numbers as you want, but we're going to have 8 zeros. 6, 7, 8. I think this will be it. So right now, we need to do for pin in. I keep wanting to write Python code. For int pin equals to 2. We start at pin 2. And then we go pin is less than 9. So we go up to 8. Then we go pin plus plus. There's our for loop. So for each one of these, what are we going to do? We are going to turn the pin. I guess we can try to turn the pin to 0 and see if this works. I guess we need to put a data type for that array list int. Yes. Lovely. That's perfect. That's exactly what we wanted. So let's just turn 2 of these pins off. And the way we're going to do it is we're going to call on 0, and we're going to call on. So we need to do this to all of these, but this is 0, 1, 2, 3, 4, 5, 6, 7. If we have pin that goes 2 to 9, how do we turn that from 0 to 7? Simple. Pin minus 2. So 2 segments should be off on that sort of figure 8. Lovely. Right. So I'm pretty close to figuring out 0. Let's see. Is it this one? Nope. It is that one. Wait. That one should be off, and that one should be on. Great. Awesome. Everything works. So we have 0. By this reckoning, we can try to create 1 and 2. So this should sort of, this code is going to be useful onwards, but we may not be able to use the 0, 1, 2 names because having, a 2-dimensional array would be more handy. But let's try to figure out 1. I have no idea what to do here. I'm just going to turn these all. I'm going to turn these 4 into 1s and see. Oh, we need to do 1 here. So I'm figuring out how to draw a number 1. Okay. Good work. So out of these 4 that are on, I need 2. Sorry, out of these 4 that are on, I need to start turning some off. So I'm going to take these 2 and see if either of them. Oh, perfect. Okay, so given that I've got so the very last light, if I remember that rightly, 1, 2, 3, 4, 5, 6. I'm gonna turn that guy off just in case. I just want to make sure I know which one of those is the one that's okay. So that is one part. The rest is gonna be over there. So I'm gonna try to turn these two to 0. Okay, one of you's gotta go. So I gotta switch. There you go. I figured out 1. So let's see if we can figure out 2. And then that will be it. You will have the knowledge required to do the same for 3, 4, 5, 6, 7, 8, 9. So let's have a think about it. So what do we want? 2 would be, in fact, I would suggest that we turn everything on for 2 and then figure out which ones to turn off. So one of the ones that we want to turn off, I think, is this one. Nope, it is that one. Yep, and we got to figure out how to remove one more. And I don't know which one that is. I'll turn the last one on. I wonder if that does anything. Nope. Okay. Let's see. Oh, there you have it. We got 0, 1, 2. So I guess if we were to write a little sequence, we could do something like this. Delay 1000, and then essentially have those 3 loops come on for 0, 1, 2. There you have it. That's a very, very useful start to our live programming the 8-segment display. In the next tutorial, we are going to be able to code for all the numbers, and we're going to do it using a 2-dimensional array. Hello and welcome. In this tutorial, we are going to be turning this random number generator into a guessing game. So the guessing game is going to work this way. The user is going to put in a number, which will be a guess. And then he's either going to be right or wrong. So the computer is randomly going to generate a number, hide it from the user. The user is going to put in a number, and then we're going to get, a little bit of a feedback. So first of all, we're going to need to create a variable, which is going to be user num. And we're going to have to somehow take this number from the user. And we're going to have to do that using the serial port. So serial.begin. We're going to need to open the serial port. And right here, the first challenge is going to be, essentially the way Arduino works is this is an infinite loop. We're going to have to stop what's going on completely. and just wait for the user to enter some information into the serial port. So to do this, we're going to basically say while serial.available. Now serial.available, it's basically it returns the number of bits or the number of bytes that are incoming on the serial port. So when you say while serial available equals to 0, it means while no information is being put into the Arduino, which in normal operation, no information is being sent to the Arduino. So you can think of this as a forever loop that's going to keep running until we enter something. So this is kind of neat. It makes the computer, makes Arduino wait for user input. So at this point, whatever we enter can be done using a serial parse int. So we can say at this stage that rand_num, the number we created, no, not rand_num, user_num. So the number that we're going to put in, that the user_num is serial.parseInt. So as long as we enter a number, the number is going to get saved inside user_num. I think maybe yep. Lovely. So just to be sure, serial.print, or actually we're going to do a more fun thing. We are going to print the user_num. So if the user enters 5, yeah, this should work. This should work. So the delay 100 shouldn't matter because the user_num is going to remain engraved. Okay, so here we are. We need to open the serial port. We really should be asking the user to enter something, but let's see if this works. I said 6. Enter. Yes, we got a 6. Okay. So we really need to tell the user something at this stage. Print serial.println. Need to use double quotation marks in Arduino. Hello, please guess a number 0 to 9. Let's try this again. But you should tell me the hello, please guess a number. Right. That needs to be above. Because right now it's waiting for the user input. So I can't ask to enter a number after I've already entered a number. This should do it. Aha. 3. There it is. 7, 8, 9, 1. Yeah, I did a totally unique one. Okay, that works. So now that we've done that, we can maybe return the user some input and see, this printing function can go right here. And then, after we've entered that, we can do a delay. So this means display number for 2 seconds. Now, we can do a little if statement after we've generated the random number. We might have even generated the random number right at the start. To make it kind of fair, we're going to generate it before. And dun 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 dun. I displayed a number for 2 seconds. So if user num double equals to rand num, I think I need to close the bracket here. Serial.print ln amazing guess and else open close bracket. We can say something like nope. And we really could print. This really should be a function, in fact. So all of this, I would suggest that all of this becomes a function. The way we can do that would be to create void show number, and then we show the number int num. Do we have a num? Nope. Sweet. Open, close, and we can digital write the num here. So right now, instead of all of this, we can just say show number. So in this case, we are actually doing the user num here. And if we get it wrong, we're going to say nope, show number, and we're going to show the rand num. And this could already work. I'm not really sure what this thing is down there. I need to make sure that the brackets close. Right. Moment of truth. So I'm gonna say 2. Nope, 7. Okay. It was 9. I'm gonna try with 7 until I get it right. This may take a while. So it was 2. 7, 4. Come on. Nope. I don't know how many guesses I'm going to need to make. I just want to make sure that occasionally it was 0. We're going to get a, it's going to be it. Statistically, I imagine if I enter at about 30, 40 numbers, it's becoming... Oh, there you go. I finally got it. It was 7. So there it is. That's sort of the basic level of the game. And I think we can improve the sort of serial print. Here, under the nope, we can just serial print nope, maybe have a space, serial.print ln. Aha, we can say nope, the number was, and that way we print out the random. That'll be nicer. And maybe we can even have a score out of 10. Int score. Score equals to 0. And if we get it right, we increment score. Score equals to score plus 1. Now, while serial number available, I guess we could have another int, which is guesses. Guesses equals to 0. And somehow we need to stop the game at 10 guesses. We could put everything into another while loop so that it all happens while guesses is less than 11, I guess. I mean, this is while guesses is less than 11. Open. Then I'm going to end it there. So that means that this is going to happen while guesses is less than 11, and then I'll increment the guesses every time the user enters a number. Okay, this should do it. And then when we're out, like, nothing happens. Like, when I write that much code, I have about 70% confidence that it's actually going to work immediately. But let's try this. 5. Now it's 7, 9. 2. I've already guessed 1, which is par for the course, pretty much good. 3, 2. There'll be 2s. Number was 0. I have a good feeling about 2. There we go. 8. So, number was 4. 6. I'll go 8 again. You can get 2 8s in a row. 1. There hasn't been a 1 yet. So how many guesses have we had? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. We've had 10 guesses. So this should be it. This should be the last guess. And there's no more questions. There's nothing. It's over. Game's up. Excellent. So when we have the game finish, I don't know about displaying this for 2 seconds. We're going to make this 1 second. So when the game is over, when we're inside the main loop, we can say serial.print let's see, double. You guessed. And then serial.print score print ln out of 10. Yeah, this ought to work, except it'll be printing it forever. I guess we can just sort of freeze it out using the while serial available over there. I mean, so this means that it'll only get printed once. So let's see. That closes that. Looks like we are good. Serial print score. Okay. Semicolons. All right. Why? Okay, I think we're good. I think we actually have a proper game now. Yeah, I think it was 7379. I'm a little bit suspicious of these numbers. So I guessed 8, then there will be a 2 coming up. Yeah, I really do think that some of these patterns repeat, which wouldn't surprise me because it was 3 after 8, and if this is correct, yep. Pseudo randomness. Many microcontrollers have the same problem. You guessed 5 out of 10. Yeah, I'm a genius. Okay. So there you have it. That is a perfectly working guess the number game, except I have a feeling that, and I'm going to retry this again. It went, I think, 793. If the same numbers come up, I have a feeling that it recurs the numbers. So in that case, we are going to have another tutorial where we attempt to fix this pseudo randomness. So I think we had 7, 9. Yeah. Wow. So there you have it. A guessing game where I can guess 100%. But nonetheless, in principle, everything works, except we're going to have to try to overcome this randomness issue right here. So I'm going to do that in the next tutorial. Okay, see you guys. Hello and welcome. In this tutorial, we are going to upgrade our Guess the Number game to solve the problem where the same sequence of numbers keeps coming up. So Arduino actually has realized that they have a problem with the random function, and they've added this thing called random seed. And it creates a pseudo number generator, which essentially tries to give you a different random sequence each time. And it does that by using the analog read. So we simply need to create an analog input and do an analog read of, I guess, A0 or some analog pin on Arduino. So let's have a look at doing that. So inside the setup, we can go pin mode, MIDI mode A0 inputs. So we can take readings from it, and then we can, I think it's random seed like this, random seed analog read A0. I think that ought to do it. And this is where the random number gets created. and we will see if we get different sequences each time. According to Arduino, that should be the case. All right, let's have a look. Five. One, yeah, pretty good. 6. 1, 0. 7. Okay, that's, and now's the moment of truth. Is it going to be 1, 0, 7? 3. That's 3, 4, 6, 1, 0, 7. And let's see if we get a completely different one this time anyway. 8. Yeah. That was simple. Beautiful. And we have a real guessing game, which gives us score. It keeps some statistics. It's a lot of fun. So at this point, I would say enjoy the guessing game. Try adding a few modifications of your own, and then you can move on to the next tutorial. See you then. Hello and welcome. In this tutorial, you're going to create a program in a circuit that measure your reaction time. So we're going to install an LED and a buzzer, and when either or both come on, you press the button and you measure how many hundredths of a second this reaction took. So first thing we're going to do is install the components onto the breadboard, and then we're going to build a counter, and then we're going to build a counter that gets interrupted with that button, which is effectively our circuit. So let's start with the button. Here we go. We grab one. So we're going to get a wire that goes into the red. We're going to need a resistor that goes into the GND. As I've said before, the value of the resistor doesn't matter very much in this case. Then finally, we get a wire to go into a digital pin. Now, I like 3 because we've just used it before. 1, 2, 3. So we're going to do that again. Next, we can set up a light. My favorite color so far has been red, so we're going to go with red again. Short leg in the minus, resistor in somewhere before, and finally a cable into the pin. Now what pin did I draw here? 9. Let's go, LED can go into 9, 8, 9. And finally a buzzer. Now let's have a quick look at where the plus is. And to be honest, this would be better served by an always-on buzzer, but we're still going to solve the problem with the one that we've got. So I think this is going to be the short leg, and that's going to go into a GND. Can go right behind. There's a ground right there. And the plus is going to go into pin 12. So the plus is going to go right next to it, and then over. Oops. Right there and over onto pin 9, 10, 11, 12. So our first goal is going to be to write a program that essentially has a counter. Then we interrupt that counter with a button. Then we introduce the light and finally the buzzer. So counter, int counter. And it can be a counter for any distance sorry, any length of time that we wish. So in the loop, I guess in the setup we can use a serial dot.print. Now serial dot begin 9600, and here we can increment the counter equals to counter plus 1, and we can serial dot print ln counter. So right now this will happen at an extremely high speed, and if we delay for a second, what you're going to see when we upload this, I will for now just save it as any random sketch. So you're going to see a counter that goes from 1, 2, 3, 4. So the reason it starts at 1 is that we increase it and then print it. So that's what the program does. Now, if we wanted to make it measure milliseconds, like thousandths of a second, now, this whole thing up to here should have only taken 1 second. So one thing we've learned is print commands take time. So you definitely want to execute this only once in the eventual program. And we may not want to measure milliseconds. We can just do with hundredths of a second. So right now, we're going to try to interrupt this count, to try to make it count until the button is pressed. So I'm going to call it int button, that's pin 3, and we're going to have an input, pin mode, button is an input, and right here, we can make all this happen while analog read button double equals to low. Right. So once the button becomes high, and only when the button becomes high, we can then serial print the reaction time. So watch this. Serial print. I guess if I leave it there, it's just going to freeze. So this is going to be just a demonstration. If I leave it in there, the count should freeze when we press the button. Watch. It's gonna go. Uh-oh. That did not work. Okay. So while analog read button is low, let's see. That is in 5V, that is in GND. So button should be low by default. And when that's not the case, we can delay 5,000. So that's the while loop. That really should work. If it doesn't, well, why did I write analog read? It's digital read. Okay. Yeah, button's either high or low. Analog read would have to be double equals to a value, 0, a less than 1 or something like that. So let's have a look at that. We should have flying numbers and a freeze when we press the button. And the freeze will only be for 5 seconds. The numbers are going to resume. Great. So we can now also say counter equals to 0. We can return to 0. So when it resumes, in a way, that's my reaction time. 34 hundredths of a second. And you can make this whole thing more accurate by moving the serial print outside of the count. So if the serial print happens there, except if we did that, we wouldn't know to press the button because the numbers are going. So at this point, we can add the LED. Int LED, LEDs are 9, and pin modes, so the LED is an output. That is very, very good. So we need to turn this LED on after some amount of time. And I guess that making that sort of time random would be really cool. So in the loop, we can say delay, and then I can say, well, since it's milliseconds, we can say random, anywhere between 3 and 8 seconds. I think we need a second bracket. So after 3 to 8 seconds, the counter is going to start. Well, when the counter starts, or right before it, we can turn on the light. Digital right, LED, comma, high. And when we stop the counter, and I don't really think we're going to need this delay to be 5 seconds. Maybe just wait an extra 2 seconds here. Okay. This could work. Watching for the light. Then we're going to press 19 hundredths of a second. It's going to come on again, though. You can 19 again. Come on, I can be faster than 19. Ah! I'm getting slower. Oh. Come on. Yes. Okay. Took me a while, but there you have it. My reaction time is about 0.18 seconds. So of course we can improve on the display style. And in fact, I'm wondering whether we should do that first or create a buzzer beep first. I don't know. See, the buzzer beep is going to be a challenge because it may itself take time, and we can't really just do it on one line. I guess we can set tone, and then we're going to press it, and when we set tone, the buzzer is going to start working. I'm going to try that. I'm going to call it int buzzer 12. What am I doing? Equals to 12. So with the buzzer set there, right here after the LED, we can do tone, buzzer, and just, you know, a pretty good 1000. We'll go with that frequency. And after the 2000, we're gonna go for the no tone buzzer. Okay. This should be interesting. Oh. Ooh. It is true. Human reaction time is better to sound, and that works beautifully. That works beautifully. I love it. So yeah, the only problem is, so if you're having something annoying like that, you can always go File, New Sketch, and just upload a blank. Or you could have pulled out the cable for the buzzer, whichever. So all we need to do now to make this game perfect is improve the print statement. So where is it? Serial.print. Right there. So .print, we can just say, hey, your time was... So print that. We can serial print the counter as well. And then you can even print counter divided by 100. Might work. And serial.print space seconds. This would have to be print ln. So I don't know if this counter divided by 100 is going to produce a working decimal, or whether I have to create a variable, which is a floating point or a long, but I imagine it will be fine. Let's go. Ah! Your time was 0 seconds. Okay. So that division isn't working. I guess... Okay, this time I'm going to pull out a cable. Which is this cable. Ah, stop it. Hundredths of a second. Done uploading. Moment of truth. $1400ths of a second. 20. I preempted that one. There you have it. Pretty good. I absolutely love it. I'm gonna keep on playing with it, and in the next tutorial I'm going to look at saving our results into an array and then printing sort of a longer set of results. So what if we had, I don't know, 4 trials of 10 attempts, and if we could print out those. Because that gets into arrays and data management, and as we advance in our usage of Arduino, what we're going to want to do is take sensor data and save it onto our computer or a device. And the first step towards that is organizing that data into arrays. So make this, enjoy it, have fun with it, and see you in the next tutorial. Hello everyone, in this tutorial we are going to take this human reaction time game and record our results into an array. So in a way we're going to get a total reaction time. We can even calculate an average reaction time over 10. But most importantly, once we get that into an array list, we can use software like Putty here to essentially download that serial output into text files and then use those to basically make graphs and interesting things with our data. So let's have a think about how we're gonna go and do this. The first thing is you want to make this loop, essentially this segment right here, which plays the game. You want to do this a limited number of times. So let's say you want to give user a number of attempts, and we can make this int attempts equals to, let's say it's 10 for argument's sake. Now we want to put all of this in a while loop. So while let's say it's 10, but we're gonna set it to 0. So while attempts is less than 10. While that is the case, we are gonna do this. And each time we do the loop, we're gonna say attempts equals to attempts plus 1. Excellent. So we're going to count up to 10 attempts, and we're going to increment attempts here, and that should mean that the loop happens exactly 10 times. So we can try this out. I suppose to make the game go faster, we need to make those 10 attempts really quick. I'm just gonna say between 3 and 5 seconds. So they'll be... Okay. I'll upload this, and hopefully in less than a minute we should be able to have 10 attempts. 1, 2, wow, that was fast. 3. Ooh, my personal best. Okay, we're halfway. New personal best. Not bad. That's it. So right now we've got those 10 attempts, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and the game essentially stops. So we can have something like int total equals to 0, and every time, you know, the counter resets, which is going to be where we set it to 0, 10, 10, 10, 10, 10. Right here we can say total equals to total plus counter. So we add them all up, and when the game is all over, we can serial dot print ln something like or maybe we can just serial print first. and say your average time was and we can say total divided by 10. And if we want to be a bit pedantic, I mean, then we can just say space hundredths of a second. Great. Okay. So we should be able to try this again and see. I forgot some semicolons. We should be able to try this out and see. Actually, this is going to print the total forever. So I think, you know, we can create like a while loop, while, you know, like while true or while one. Dun, dun, dun. So this is basically going to stop here forever. The game, the game's just going to end here after this gets printed. So the interesting thing will be if there's any conversion issues, because that in itself is going to be a decimal. Is going to be a decimal number almost certainly. So let's find out. Okay, exciting times. Will we get a average that makes sense? 16. Good boy. Come on. No! That was bad. That's equal personal best. I preemptively pressed it. 12. So I don't know what to expect. Maybe 28, 30 average. Come on. Your average time was 29 hundredths of a second. This is awesome. So we're going to do this at least another time. So we're going to find out if we get some type of an error with this. But so far it looks really good. So the only thing that I want to do right now is to create a basically a list array. And we're going to call it results. And since we're running the whole game 10 times, we're going to make this array 10 large. So we need to write into this array, and then hopefully at the end we can print the array. Now, the way you print the arrays with, you know, C or Arduino, you actually have to use a loop to cycle through individual elements. So we're going to have to add that after the average statement. So how do we add to the array? We can use the attempts variable. So let's just see where we sort of print the user time. Serial print counter. There you have it, right there. So anywhere inside this section of the code, we can add a statement that writes to the array. And we can do it right before we reset the counter. So we can call it results attempts. Now, you know, in this case, I almost think it would have been better if we called attempts attempt. But it doesn't matter. In fact, I'm just looking to see how many times it's used. Let's see if I there you go. I think that's everything. So results. Okay. Great, that works. So now I need to print out the results. Shh. Oh, the program is running. So I better pull out the that. And we can get onto the loop that prints out the result. So, when are we going to print it out? We can print it out at this point. We don't even have to check if the number of attempts was a certain, because to get here, we would have played exactly 10 times. So we can simply say for, and we just make a for loop for 10. For int I equals to 0, I less than 10, I plus plus, open close bracket, 10. What do? We just say serial.print results. So we print the ith member of results. That should get just get, 10 numbers. They're all going to be 2-digit because I can't crack like 10 hundredths of a second. And then I can separate them by commas. Comma. And I think that'll do. I think we're going to have an array called results that we can strategically strip eventually using putty. But most importantly, our goals are to have an array and to have the average. So the average is already successful. Let's see if the array is going to make sense. No! I'm going to have to restart this game because I think we just reopened that and it restarts. Let's go. Come on. No! With a time that bad. No, I'm going to restart this. Come on. Yeah. Let's average like 16. That would be amazing. 15. Come on. 15. Yeah, so far so good. Ooh. Yes. Goal was 16. That can be achieved. Ooh. Come on, 12. 16. Pretty good. Your average time was 1/100th of a second. Right. I think we may need a variable called average. And we may need to make it a floating point. Float average equals to 0. And where is it that we print the average? Right. Now we can say average equals to total over 10. And then we print the average. Because the average is a floating point, it'll be able to save the decimal. So last time we must have gotten lucky that whatever number we had was perfectly divisible by 10. Is there anything I can do? Sure, I can make the attempts come even faster. So we just need to fix that average and we'll be good. 14th. Good. Oh, horrible. Come on. The average time was 1.00. Maybe we can print the total, serial.print, and we'll print it in a separate line, print ln, and we can print total. And we'll see if the total number makes sense, because right now, the average, I mean, that really has to work. So unless, I don't know, unless the total is somehow wrong, I can't think of why this wouldn't be working. So, in the interest of time, I'm going to speed this up really fast. I won't be able to perform that well, but at least we're going to find out through this process of debugging if this total computes correctly. I can only imagine that it does, because it won't go out of bounds. All of these things are global variables. So the only thing is, I think this division here is being a bit of an issue. So let's have a look if this is going to work. If it doesn't, you know, we can manually move the decimal point and figure out the average. But let's just see that this thing makes sense. Let's go. By the way, I'm not competitive with my times. I'm just going to, they'll come too fast. Okay. There you go. This is the core problem. The total hasn't been adding up properly. So total is 0 here. We have a counter, and the counter is going to be different every time, and if we add counter to the total, we should end up with, you know, 200 something, 180 something. But for some reason, we don't. And that doesn't quite make sense. I mean, the only thing that I can think of was that the counter is somehow set to 0 when it's added here. But, you know, we're doing this line pretty much where we print out the counter, and the counter is, you know, a 2-digit number. So the total is never reset to 0. Yeah, by all means, this should work. I've just moved it over here. The only other thing that I can think of is we can ignore the total in this area. So the only thing that I can think of is somehow this total isn't doing the job. And frankly, I don't entirely understand why. We can try to add it up inside this loop and just say total equals to total plus results I. So those are the sort of individual results. And if the total is an int, oh, total itself should be no, it shouldn't be a float. It should be an int. These are all round numbers. So we're adding these integers together. I'm guessing if we're going to create a float operation, we can try and make the total a float as well. So then we divide a float by a float, which, you know, should be operations with the same type should work better. So time to find out if this is going to work. We're going to print that total in the very last line instead. And, you know, actually, since we're there, who knows? Maybe this is going to work as well. Moment of truth. Okay, come on. Oh, actually, open this up. I'm pretty good when I'm like casual. Yes, 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 it worked. Okay. So finally, I can say serial print, and I can right here say your average was, and that is going to work beautifully. We can delete the average. So as long as that total was a float, as long as you divide a float, you can get a float. That's not an issue. The issue is when it's an integer, you know, Arduino doesn't dynamically convert types, which I'm making a mistake, probably because I used way too much Python lately. Shh. Okay. So last debugging fixes. Average was not declared in the scope. Yes, get rid of the average. Time for some fun. Bah, no, I wanna be better than that. Okay. Yeah, this remains. This is your average time was 1460, and I can add the hundredths of a second at the very last, and I can make that serial print, and that's it. I will run it one last time, even though it's not necessary, just to show you that this is it. The game works perfectly. Here we go. My stellar performance is going to be ruined by the first one. There you go. Your average time was 18.8 hundredths of a second. And there you have it, ladies and gentlemen. That is the reaction time game with arrays and averages and data tracking. Have fun with it and see you in the next tutorial. Hello and welcome. In this tutorial, we're going to create a memory game circuit. So essentially, we're going to set up the memory game, which is going to have 4 buttons and 4 LEDs. Now, I'm going to start building the circuit and following the schematic, and then I'm going to zoom in. The idea is essentially simple. We have 4 LEDs that are going to flash randomly, and then the user is going to try to repeat that sequence by pressing these 4 buttons. So let's get started. Oops. That's a tough one. Jeez. Okay. So we're gonna get the buttons in first. I'm going to try to distribute them such that they are across middle of the channel, going up relatively all the way. Yep. Maybe move this guy over by 1. Okay. So I'm going to zoom in a second, but the idea is pretty simple. We're going to connect the buttons first. They're going to go one leg to 5V and one to the G and D through a resistor, which I didn't mark on this schematic because the grounding isn't necessarily marked usually on schematics, and it would sort of spoil my view here. But okay, let's zoom in and you can follow after me. So the red wires are going to go onto the upper leg. So red in there, in there, in there, in there. In there. Here we go. So now for the resistors, into the earth and the other leg. Now I've said this a few times already. I may sound like a parrot, but the size of these resistors doesn't really matter. Now for the LEDs. So we want to put them in between the buttons, and the only thing we care about is getting the short leg into the minus, essentially. Right there. So right next to the red. I think we're always going to have some space. I'm going to go 2 green, 2 yellow. I have a theory that this is going to be easier to remember when there's 2 different colors. The theory could be wrong. Lovely. Okay. Now these resistors are going to get closer to the LEDs. You got to watch out that it's the same row. So we got 16. Ah. How in the world? Oh. Yep. That is... I think it's the same leg as the button. That's what's going on. Right. And last but not least, there we go. So at this point, we've got 8 wires to connect. I'm going to use some color coding, and I'm going to use some nomenclature. So we're going to get basically buttons into even numbers. So this is going to be 0, 1, 2. We're going to start from 2, and we're going to connect 2 to this button. In fact, I'm going to move everything over to the edge. Kind of have these wires interfere as little as possible. So therefore 3 is going to go into the LED. There. Maybe I can do it from the other side. Now the green is going to go into the button again. So we've got 7 and 8 is going to be the last one. So we got this button connected to the green, this button connected to the green. Actually, it should be over there. That button connected to the green. So this guy is going to have the LED. Number 8 is going to be the button, and number 9 is going to be the last LED. I'm going to have a pretty awesome. There you have it. I may just use one of those clamps that I had lying about to make this whole thing look a bit neat. You know where everything goes. Lovely. Okay, so what are we, 8 minutes in? At this point, I'm just going to declare the LEDs as outputs. I'm going to turn them all on, troubleshoot if there's any problems. Right. I'm actually not going to name the LEDs. I'm thinking we just create a straightforward pin mode. 2 is an input. We start off with an input. 2 input. Then pin mode 3 is going to be an output, and then we're going to repeat this 4 times. 2, 3, 4, 5, 6, 7, 8, 9. That ought to do it. And just to make sure that everything works, digital write to high. No, wait, we're dealing with 3. So it's going to be 3579. And this is basically going to tell us that all the LEDs work. I'm going to temporarily save it as that. Yep, all 4 LEDs are on. It's quite interesting to me that the yellows seem brighter, especially on camera. When I'm looking at them, not that much. Okay, so we essentially have a circuit that's ready to go. The setting up of the actual game, where the lights come on in random sequences, is going to be a bit trickier. We're going to need some arrays, some random numbers, and we're going to handle that in the memory game, which we're going to program in detail in the next tutorial. Hello and welcome. So in this tutorial, we're going to try to make at least a basic level of a memory training game. So that's going to entail these guys blinking a random number of times. If you haven't noticed, I changed it from green to red. It's kind of better on camera. That's pretty much the main reason. So let's first get the pin modes out. We're gonna need to have 2, 4, 6, 8 as inputs. That's where our buttons are, and then 3, 5, 7, 9 as outputs. So we're gonna have pin mode 2 input and pin mode 3 is gonna be output. And we can kind of repeat this 1, 2, 3. So we have 4, so now we can go 4, 5, 6, 7, 8, 9. Beautiful. So let's now have all of these LEDs blink a random number of times. How are we going to do that? Well, let's start by setting up the random seed. We've learned from the past a 0. And probably better to set analog pin mode A0. I don't think you have to set it as an input, but I think it's better that we do. So we've got that random ready. Now, we can digital write. So we've got 3 high. Now to get it to blink, well, I really think it would be better if we maybe had some type of a function. By the way, I'm doing all of this in the loop, and really I should have been doing this in the setup, but that's pretty easy to change. So if I get LEDs to blink, I think that's best done in a function. And I'm going to do it inside the setup, actually, because in the loop, I'm going to check if the right number of blinks was achieved. So I'm going to create a function, void blink. Blink is already existing. Okay, wink. Void wink. Now, this wink is going to have, I'm guessing, what are we going to need? We're going to need the number of the pin, so int LED, and we're going to need the number of times. We call it int times. So I guess that would be a pretty simple for loop for int I equals to 0. I is less than times. That's how many times it's gonna blink. I plus plus. Oh, plus I plus plus. Come on. So we've got this for loop, and in the for loop, we can digital right? Now, instead of writing an LED number, this is the input of our function. We're going to say wink 2,7. That means LED 2 7 times. So digital, right? LED, comma, high. Then we gotta make an arbitrary delay. I like 200. It's kind of countable. Maybe a bit more. 250. That's 2 blinks a second. Yeah. And then you do the same, but you turn it low. Now, if I have programmed that correctly, by the way, Control T formats our code. Very nice. If I've programmed that correctly, I should be able to say wink. Wait, 27, LED goes first. Wink. So we've got 3579. Okay, 3, 5. Semicolons are there. Okay, so if I've programmed this right, when I upload this, it's going to wink int I. If I've programmed this right, it's going to blink the first LED. That one, it's going to blink it, what, 5 times? Beautiful. Okay. Now, we can do this to all the LEDs, and except we're going to need to randomize the amount of times that we blink. And then we're going to have to, like, make sure that those, random counts can be checked inside the loop. So I think we're going to need some global variables. That's the only way I can do it. So I guess I can call it LED1 blinks. And then that's going to be an int. I mean, we don't have to initialize it. We can just do it like this. And then we're going to have to set it to a random number. And no, let's make it achievable. Should we say 0 to 3? 0 to 5. Okay. So one, 2, 3, 4. So right now, after I've replaced that with these, I'm going to have each of the LEDs in sequence blink a random number of times, with it being a maximum of 4, I think. Let's try this out. Okay, that works beautifully. Now, I'm just gonna 0, 1, 2. For testing purposes, I'm gonna lower these, and then we're gonna write a little loop which essentially checks that we've sort of guess the right number of times. So first thing we want to do is if digital read, I guess 2 would be the first button, double equals to high, we're gonna need to have some kind of a counter that tells us that we're gonna have to count how many times we press this button and then compare that to how many times the LED blinked. I don't see an alternative to creating 4 more global variables. What are we gonna call them? I guess count 1. That's fairly brief. Count 1. Then count 2, 3, 4, 5. Okay. So this time, since we're going to iterate them, we definitely need to initialize them to 0, because if they have any value other than 0 at the start, that's going to get our whole program to be wrong. So, count. That means we increase count 1 by 1, and we're going to delay half a second. So we're going to need to press these buttons, maybe 700. We're going to need to press these buttons once and let go. Okay, so that being the if statement, we can again clone this. Okay, Control T sorts us out, make sure we've got the right number of brackets, and aha, that guy there looks like a nested if. Control T. Beautiful. So we got 2, 4, 6, 8. And we're going to have count 2, count 3, count 4. All right. And we win if all the counts are correct. I'm going to need one more massive if statement here. So if all the counts match up against the blinks, so the blinks are randomly set at the start, and the counts are you're pressing the button. So this is going to be a very big if statement. It's going to be, you're going to be comparing count 1 double equals to LED 1 blinks. And this is how you do AND in Arduino. So it's going to be 4, 4, 3, 3, 2, 2. If that is the case, what then? Well, we should celebrate. If that is the case, we can, I don't know, digital write all LEDs high, I guess, and block the game. All right, so that's that if statement. So the LEDs are 3579. 3, 5, 7. So this code, I believe it's actually gonna work. Lots of copying and pasting. Control T sorts this out. That's the if statement. That's that. That's that. Okay. So follow with me right here. We're gonna have to count how many times each of these LEDs blink. And then we're gonna have to repeat that with the buttons. If we succeed, all the LEDs are gonna come on. The B4 B links. Wow. 1, 1, 2. 1, 2. Uh-oh. Let's try that again. Just 2 there. 1. Success! The program definitely works. Okay. Let's try this one more time. One. Yes! And you can make it as hard as you want. And this is what I like about this game. At 5, it already becomes tricky. I don't know if I'll be able to pull this off. Three, 1, 2, 3, 1, 2, 3, 4, 1, and 1. Yes! So you can try this at home. Try this with higher and higher numbers. See how good you can get. It's basically been a lot easier than I expected. However, it's taken a lot more code than I expected. So in the future, we're going to save our results to arrays, and I'm going to have a look at systematizing this to sort of all happen within one loop or some type of array convention where the random blinks are read from an array. It's going to be harder, but hopefully a bit more compact. Okay, see you in the next tutorial. Hello and welcome. This is the module introduction for module 5 using sensor libraries. Now, sensor libraries are simply a tool that makes Arduino easier to use with really advanced equipment. Let's say you have this along with an infrared receiver. Now, this is an infrared remote control. To basically write code which is going to measure the outputs of that receiver, convert it to a unique number, you may need 100 lines of code and a knowledge of some really high-level concepts. With a library, you just use a given function and get the job done in a couple of lines. So that's why they're there. Now, in this module, you're going to look at libraries for 2 types of equipment. One is, as I said, infrared remote controls and receivers, and the other is MPU 6050 gyro accelerometers. So that's all I gotta say for this intro. I'll see you in this tutorial. Hello and welcome. So in this tutorial, we are going to be using a remote control, an infrared receiver, to control that set of lights that's still there from our sound sensing, bouncing music bars. So how are we going to do that? And the short answer is using an infrared remote library. Now, a library Well, a library is a sort of set of semi-hidden code where you have some complex problem that is solved, and instead of you engaging with the entire problem, you're only using a couple of the functions that the library produces. So, in effect, you go from your capacity to understand every aspect of a particular circuit or a particular program to being able to use certain inputs to produce certain outputs. It highly empowers the user to do amazing things, but it also more or less always leads to a somewhat lower level of understanding. But if you are a veteran, you can go into the GitHub. This is going to be attached as a link, and you can look into the various files, examples, and everything that goes into this library. I mean, there are 309 commits, so 309 versions. There's 39 people working on it. So, as you can imagine, this is no trivial piece of work. So, having told you this caveat about library being a black box, let's just see how we can use this black box. So you go inside GitHub, inside the Arduino IR remote, and you download a zip file. At this point, you go into your Arduino. I've already pre-written some code, and you go into Sketch, Include Library, Add Zip Library. You can go into your downloads, and if you go into your sort of latest downloads, come on, man, what's up? Keeps wanting to rename it. If you go into your latest downloads, surely I'll be able to get into my downloads. Documents, downloads. So if you go into your latest downloads, which you can go details, date, modified, there you go. I downloaded the library twice. You can just click on it and click open. So once you do, you're going to get this IR remote.h, and typically speaking, if you go into File, Examples, IR remote, there are a whole lot of examples that come ready with this library. So you can just upload that code and try to make it work with a particular circuit. But we're going to make this ourselves. So just going back into the PJRC site, so let's walk ourselves through some basic commands, some basic functions in this library. So IRECV, this line right here, assigns a receiver pin. So we are going to receive on pin 11, and so we have already set IRECV, Arduino. So we already said IRECV pin is 11. So right here, we assign pin 11 as the receiving pin. Next up, you enable it, and we enable it inside the void setup. Next up, IRECV decode results. So this essentially creates a temporary variable called results, inside which whatever is received, a unique number, and there are multiple conventions. You can have a decimal, a hexadecimal number, and this number again is going to depend on the brand of the controller, and this library controls multiple brands. So the code results right here sets up a variable to store unique number. And that essentially here enables receiving. So at this stage, we have done the entire setup. So right now we need to basically write an if statement saying if there is a result that comes in, we want to print it. And to print it, we're going to need the serial serial.begin 9600, and we're going to have to do that if statement here. So this is a Boolean. So this is just if irrecv.decode and then pointer results. So this is a true or false. If there is a result, if something's written in, then this is true. So if that is true, we can serial.println, and we can print results.value. And this value can be various formats. So we're just going to go with hexadecimal. And that should do it. There is also an IRECV resume, which gets us ready to receive another code. But once I upload this, we should be ready to receive a number and print it. I don't think it's going to work twice, but it's definitely going to work. So, wow, I'm optimistic. Yeah, it's going to work once we plug this guy in. So we need to go into pin 11. By the way, if you want to look at one last link, there's a DF robot example, and here you see that once it faces you, the rightmost pin is 5E, the middle is G and D, and that last guy is going to be our signal. So he's going to go into pin 11. So that's going to be 13, 12, 11. Okay, so that's pretty much all the circuit. I think we're good to go to try out if we can receive a unique code. So I'm just going to press volume plus, and we should see one line of code. Oops. All right, we're seeing infinite lines of code. So in the very next line, I think we should go irecv.resume. And this function right here just sort of resets the receiver and gets it ready to receive another code. So hopefully that's not working. So let's see. Perhaps, oh, we haven't really opened up that if statement, and I think this ought to do it. So Control T to format it. What happened was that these two are not inside that same if statement, and they should be. So unique number, unique number. So FFF is like probably what happens when IRECV resume gets executed. Because it literally happens if I hold the same number for a bit longer. So if I try to just press a little bit, I get a unique number every time. And if I hold for longer, I get this FFFFF. And I think FFFFF is like a 0 in hexadecimal. So, okay, I think we're good to go. I think we can, right now, just write another if statement and say if results the value is equal to something that I press. Right now, I'm just going to go with the power button. So, power button. That's the power button. FD00FF. So, if results dot value double equals to that, and what am I gonna do? I'm just gonna turn on all the lights. So for int I equals 2. So our lights are actually they've been switched over, so they're from 2 to 7. 2, 3, 4, 5, 6, 7. That's 6 lights. Int I equals to 2. I is less equal to 7. And then we're gonna iterate. So from 2 to 7. Oh, I need to do the same to basically set them up in setup. So here's my for loop. Digital right I comma high. Okay, so that's gonna turn on lights. Not really. That's gonna turn them on after I make them exist. And this is going to be, I'm just going to copy this for loop and I'm going to use it for pin mode. Pin mode, this is going to be output, and I'm going to pin mode all of these to output. And why, my man? Okay, exit status was not declared. But results.value. But it's a unique number. So that should close that if. And that should have that loop. If we put quotation marks around it, or double quotation marks, I don't believe it's going to be taken in as an integer. This is... yeah, this is going to work, but I don't think it's going to actually turn our lights on. So that is results.value, but it is not being read. There is a trick that I've seen with hexadecimal. Don't ask me how this works, but you go 0 and then lowercase x. Okay, so I'm going to press the wrong button and the right button, and the lights went on. Okay, we're winning. So we can have an on button. I guess we're going to have an off button now. We're going to choose 0. So 0 is going to be our off button. And I'm just going to copy this if statement, put it there, Control T, make sure everything is formatted nicely, and I'm going to go low. So I need to actually figure out what the number for 0 is. So let's have a look. Here we go, 0. Okay, so we're going to use the 0x again. Moment of truth. On. Oops. This should be on. And 0 should be off. Works. On. Off. On. Off. On. Off. That's a lot of fun. Okay, so there you have it. That is the most basic code for the infrared remote. In the next tutorial, I will escalate the fun. I will add a loudspeaker, and I'm going to use this to turn the loudspeaker on and off, and I'm going to also use it to select a frequency for that loudspeaker. So, see you then. Hello and welcome. In this tutorial we'll be using an infrared remote and that infrared receiver to play around with our speaker and lights simultaneously. Now what is really interesting and surprising to me is that we cannot use the tone library, and the tone library, as we found out, does the coolest sounds with the speaker. It basically interferes with PWM, and the infrared remote library uses some of those PWM functions. So we're gonna need to get creative. So my first goal is really going to be just taking this pin 8, labeling it as an output, and having a sound play when I use the remote. So let's get started. So this is the pin 8. So this is going to be the speaker output. And here it is. It's set as an output. And now we're gonna read a button press. That's gonna turn it on. Come on. Yes. 0 is gonna turn it off. And play button, FTA05F. So this is the one we're going to copy and paste. I'll just put it out there. Then I'll copy an if statement. Control T. Alright, we get rid of that for loop. That if ends there. Does that end the loop? No, the loop never ends, so we're 1 bracket short. Good. So that is our code, and when that code is called, we can speaker high, delay 5, and then we can digital write speaker, oops, make that low. Okay, let's have a try. Well, FDA 05F. Okay. If we're inside that other results value loop, so I think that needs to close. We need to go Control T. So now we're an even keel. We have one too many over there. I think this is gonna work. And first test, just come on, lights off. Good. And I think these loops are, it'll only enter one of them. So I like what is going on. So right now, all I need to do is have some type of a variable for this delay, int pause, and then I can have maybe a level up and a level down. So that should be pretty easy. So I have int pause. We're gonna set that as a default. We're gonna set it to 20. And we're going to have 2 more if statements. And I guess these guys are easier to copy. Get rid of that. Pause equals to pause plus 1, and the other one's going to be pause equals to pause minus 1. Of course, we need to figure out which buttons we're going to use. And I think there's like a volume up, a volume down button. So we can use those. If I, right here, have a look, there's a, on this side right there under my finger, that there is a volume up, and there's a volume down as well. So this is going to be, I guess we're going to go the pause up and the pause down. So down is going to be louder, paradoxically, but I'm going to press down. And by the way, there's interference. If you aim far away from your detector, you can get some weird numbers that are not what your detector wants to detect. So FD10EF, Control C. So this is going to be the down button. And that 50. This is going to be the up button. Okay. And finally, oh, Control T, what the monkey business. Okay, these ifs are all in line. Personally, I would probably have these a little bit more compact and have these in front of cut and have these in front of that. Yep, that works. I don't know why that's there like that, but that's much nicer. Okay. I like. So now that delay is just going to be pause. And to be on the cool side, we can print the pause. Pause. All right. Awesomeness. Okay. On, off, sound. Now, lower sound? What's going on? Minus 4,000? What? Alright, let's try that again. 20. Right, 20. Now we're going to go higher delay. 2007. Alright, so what's going on is that it doesn't go up by 1, it goes up infinitely. And I have a feeling that 1, we could put some delays here, but 2, and this is really hard to perceive, I think that these if statements, I'm going to cut them again, and I wonder what would happen if we pasted them, Control T, if we pasted them inside the if of what happens when we receive results. Because the way I see it, for every receipt, this is going to go up by 1, right? So I think this is going to work. What was going on is that this increase was inside the loop. So it was going up thousands and thousands of times. So let's try this one again. Okay, good. Now. Okay, so it's knocking it down. So we can go down to like 7. So down 1 play. Cool. So, look, I think that's almost as far as we can go. One thing that I guess could be sort of good would be to vary the frequency. So let's just say, for the argument's sake, we just start at 6. And these LEDs that go on with the on button right here, where they all turn off and all turn on, I can take this statement for all of them turning on. So I can cut, and maybe I can put that in the main body of the loop. And, you know, forget about if the results value. There's no results value at all. So I can just turn on the same number of LEDs as the pause. And I'm just thinking Control T. Yeah, that fits. And then you can turn off the same ones. You can turn off all of them, but with no delay. So then you could put a delay here. And then you can turn off all of them with no delay. And I think what that's going to do is basically, you know, have us have the same number of LEDs as the pause that we're using. So, moment of truth. So that should be, So now we're going one LED up, one LED down. That's pretty nice. I'm going with the up and down keys. And that's kind of fun. So that's 6 LEDs. Okay, clearly there is an issue with this guy interfering, this delay right here. If it was delay 1, we may just work. Now, so if I go inside and have a look what happens here with the values, I press play, it's 6. When I go down 1, it should be 5. Wow, that's a very interesting visual effect you're seeing on camera, because I can't see it by looking at the LEDs. So what we got was a hybrid, because this delay right here kind of got in the way of turning the buzzers on the speaker on and off. So in a way, it made the pause of 1 millisecond the same as it would be for 2. But other than that, we got what we were looking for, and it's a lot of fun. So I suggest that you guys try this out. Go back into your circuit. We had, you know, remember the piano sound effects? All of these sound effects actually used, not all of them. The space gun, for example, didn't. So you should be able to very easily copy and paste the space gun function and then have it triggered by this remote control. Fibonacci unfortunately used stone, so that's not going to work, but you should be able to go back to some of the stuff we covered and recycle some of that code, which should be a lot of fun for you. Okay, I will leave it at that and see you guys in the next tutorial. Hello and welcome. In this tutorial, we're going to wire and read readings from the MPU 6050 gyro accelerometer. So a gyroscope is a device that detects tilt and turning. An accelerometer is a device that detects force. In my mind, accelerometers are a lot more interesting. So essentially an accelerometer would be able to, if you placed it still, would be able to detect gravity and the absence of gravity for once. So the idea is I'm going to place this gyro accelerometer on this cube, and we're going to turn it at different angles, and we're going to see this actually in effect. You're going to see how gravity is distributed if this is tilted and how it's distributed if it's still. But first of all, we're looking at a fairly simple circuit diagram here, but we're looking at two different libraries. DFRobot comes up with this example code on its wiki. I am going to do something a bit simpler. So I'm not going to use the wire.h library. So we're going to use the I2C dev and the MPU 6050. Essentially, those are the same libraries. I2C devlib is a family of libraries for various accelerometers, MPU 6050 being just one of them. And very soon the support is coming for multiple platforms. At the moment, they only work with Arduino. So what you want to do if you don't have these already is go to this wiki and install from this zip the library. So you're going to go into Tools, Sketch, Include Library, Add Zip Library, and browse to where those were downloaded. So let's get to the schematic. Pretty straightforward. I've got cables that are almost color-coded with the image there. The red cable is going to go into the 5E. The black is going to go into GND. The green is going to go into 4, and the white is going to go into 5. So I'll just go in so you see it. VIN to 5E, G to GND. SDA is the green one. That's going to go into number 4, and SCL into number 5. Then I'm just going to place this on this cube so that we can actually more easily detect angles. Put this cube down. Excellent. All right, so let's write some simple code. So, as I said already, the I2C dev library is the first one, and then there is actually a specific MPU 6050 library, which looks like this MPU 6050.h, and that needs to be hashtag include. You can't put these on the same line. For some reason, I tried to compress the code earlier, and then you essentially set the device for the I2C dev to MPU 6050, and this is the code that you write: MPU 6050 accel gyro plunk. Then you write a 16-bit integer, and you create essentially all of them for the accelerometer and gyroscope. So AX, AY, AZ. So that's the 3 for the accelerometer, and then GX, G, Y, G, Z. Next up, we are good to go with the setup. We're going to serial.begin. We'll try 9600. And we're going to do Excel gyro.initialize. Initialize. Okay. That's that. And with one command, these 6 variables are all going to be supplied. So that's Excel gyro.get motion, and then at ax comma at ayaz x y z gx gy gz. So right now, we should, in theory, have values that we could just simply serial dot print ax, for example, and we can delay a second. This should, in theory, work. Gonna save it as a random sketch. Initialize. I think there's a 6 going in here. Oh, 9,600. Yay! So we can put that into ln, and so there you have it. So we should be able to change these values. Right. And I think a much fuller picture will happen if we actually print out all 3. So serial, accelerometer x, and then ax. We can print all of them and make a bit of a shorter delay. And make that just 100. And maybe serial.print ln. So let's see how that looks like. And okay, get rid of the auto scroll. So as you can see, the Z, that being the gravity, the Z is like 15,000 something. So I want to get this primed so that you see, I'll make this at like 0.3 of a second. Watch this. So Z, you're looking at it, 15,000. We're going to turn this around. Now Z is nothing but Y is minus 16,000. If we put it this way, Y is 16,000, which leaves X to be this way. So right now X is minus 15 and X is plus 16. And if we shake it, well, obviously the forces get distributed differently. So that is the amazing accelerometer sensor. We can do the same. I guess we can just copy and paste this to get the gyroscope. So, gyroscope. Gyroscope X, Y, Z and G, X, G, Y, G, Z. And the gyroscope actually responds to turning. It's kind of hard to follow this, but if you turn it, you're going to see the gyroscope values change. So in the next tutorial, I will look at putting in 3 LEDs and playing a little bit with the accelerometer. We may have to change the camera setup to zoom out a little, but I shall see you then. Hello and welcome to the module introduction for the final module, module number 6, data analysis and visualization with Arduino. Now, as the title says, the module is all about sensor data, how to save it onto SD cards, for example, and how to represent it visually. Now, what we do to achieve this is access a software called Processing, which is another open source project, which basically is going to take live readings from Arduino serial monitor, of all places, and turn those into moving graphs. And why this is in particular useful is because a lot of automation and a lot of devices use sensor input to directly control an output. Now, it takes a sort of visual representation of that input to see how stable it is and perhaps to do some refinement, averaging, etc. To make that project work. Now, an example of a project that really could use some sensor visualization, you can have like those self-balancing robots and segways. Okay, so much for the introduction. I will see you guys in there. Hello and welcome. In this tutorial, we're going to be learning how to use Processing. Now, Processing is a visualization software and it can interface with Arduino, and most interestingly, it can graph serial values. Now, we can take any sensor output and send it to the serial and then have like a very, very cool graph that tells us what's going on. In fact, where I am heading with this is that we're going to be visualizing the outputs of gyroscopes and accelerometers. Very, very exciting. Now, there is a learning curve here, and I'm not going to go into the details of how Processing works. I am initially going to set up a very, very basic tutorial which sends hello world from Arduino to Processing and sends 0 and 1 from Processing to Arduino, which is going to turn on and off an LED. And I'm just going to copy the very first tutorial from this link. It's from Spark 1 connecting Arduino to Processing. I could have done this myself, but I'm not a big fan of reinventing the wheel. And I think this is an excellent tutorial, so link will be in the description. If somehow I forget it, just freeze the screen and type this in. Now, there is Processing, there is Arduino. This is going to be off the screen, so I'll be copying and pasting the same code that is 100% available to you. I will only do this for the processing. So, we start off by including the serial library. So that is either in Sketch or Tools, import library serial. So after that, funnily enough, it has also a void setup, just like Arduino. After that, we create these variables. My port is a variable of the serial type, and val is a string, nothing else. Then we have a setup. This is a very, very key piece of information right here. This is the only thing you will all have to change. Well, not all of you. Some of you may be at 0. We have tools. And right here, we see that we're using like the second port. Now, the second port, computers start counting from 0. So the second port is the first, like number 1 in the list. So it's 0 is the first, 1 is the second port. And then we have a void draw code. And all it does is just says, hey, if port is available, read until new line, and then print whatever is printed. So here we can, serial.begin 9600. By the way, this one's also operating on 9600 board. We can check that we are by going there, 9600. And we can now go serial.println. And you print anything you want. Yeah. I don't know if anybody gets the Floyd Mayweather reference. So we can delay half a second. Boom. So when we upload this, we should see a series of hello worlds or yeahs. And now if I load processing, and there they are, they're being printed like an endless row of yeahs. So it's successfully reading the serial monitor. You'll notice I can't open the serial monitor. It shows me like an error. So error opening COM5 is busy. So that is all you need to know for the very start. In the next tutorial, we are going to be doing this the other way. We're going to be taking this program and we're going to be sending out a 1 or a 0 constantly. And then we can turn a light, an LED on or off based on whether, we're sending a 1 or a 0. So let's do that then, but that's all for now. Hello and welcome. So in this tutorial, we are going to modify our last programs to have processing here send a 0 or a 1 to Arduino, and then to have Arduino turn on an LED depending on whether it receives 0 or a 1. So let's start with processing. All that I really want to do right here is create like a bit of a window in the setup. So here we're going to draw a size, 200 by 200. That there draws a window. Draws a window. So if I run this, we should be able to see, there it is, that is a little window. So that draws a little window, and then we're gonna have something happen if that window is clicked. Now, there is, instead of if port available, we can basically switch that and say if mouse pressed. If mouse pressed double equals to true. If mouse pressed is true, we can say that here. If if mouse is pressed, then we can write a value in my port. So if that is true, I don't know, can open the curly braces here. We can my port dot write. I wonder if Control T works. Yeah, it does. Although I have to get rid of that Control T. You get rid of all the braces. The Control T does too much. We need to have more brackets. What are you joking about? Oh, no, the bracket's already there. So if mouse is pressed, that the brackets were already there. So if mouse is pressed, then we're gonna my port write, and we're going to write a string of 1. So then we're going to print ln so we're going to print it down here just to see if it's working, and this is what's going to go to the serial. So this is the key line. Send string quotation marks 1 to the serial. So, and if we don't do that, then we can I wonder how Control T does that. I don't know why you would indent this. Yeah, because they're not. So, otherwise, we are going to my port dot write 0. So we're either sending a 1 or a 0. Okay. So I need to make sure that, yeah, we need one more curly brace. Control T. All right. Everything looks in order. I prefer maybe this else to be like that. So right now, when we click this, we're sending a 1. Otherwise, we are sending a 0. In fact, if I wrote print 0 here, what you would see is an endless line of zeros when this program is run. Be 0, 0, 0, and then you press the thing, and now it's 1s, and then it's 0s, and then it's 1s, and so on and so on. So let's have a look at modifying this code so that we can read it and turn an LED on or off. So we can have a character val equals to, we can just store it as that. We can have an LED pin, and I can put that in pin 3. And I think that's all the variables we need. We need to go pin mode, LED pin is an output. All right, serial is working, but this time we're gonna need to check if the serial is available. So if serial.available. As I have already taught you, that is a true or false statement, and serial.available is a function, so it has to have these open close brackets. It returns true or false, so if serial is available, then we're going to do whatever it is that we're going to do. If it's available, we can read a value, and we can serial.read. And then depending on whether that value is 1 or 0, if val double equals to, and I think Arduino is going to be insisting on double brackets. If val double equals to 1, what then? Then we digital write LED pin to high. So you don't have to, and then you can else LED pin to low. You can put a little bit of a delay here, and you can make the brackets around if and else if you feel like. You can delay 10. So what this is gonna do is hopefully read that value from there and turn the lights on or off depending on whether this works out. So I'm gonna Control T, see if I got too many or too few brackets. Now everything looks good. Serial.read, I think that needs a semicolon. So, oh. We need to upload this. Else. Yeah. What am I doing? This is gonna work like this, I'm pretty sure. Except I'm gonna put in the curly braces. We may have to stop that to upload this. Yay, finally. All right. So we don't have a pin yet. We don't have an LED. That should be really easy to accomplish. There we go. There's a resistor. We can test immediately if it's the resistor of the right dimension. Yes. Point you up there, son. So, what did we say? Pin 3. 0, 1, 2, 3. Okay. Moment of truth. Not working. I don't know. You can put it, make it maybe match those up. I can add the open close curly braces. But I'm not really sure what the deal is. Oh, there it is. I click the mouse and the light goes on. Pretty cool, huh? So I guess I'm just going to do a little bit of an investigation here. I will use double quotation marks and I'll upload that. And we gotta stop that. Make sure that works. I don't... Okay. Wow. So there you go. I don't know if... having it work like this would have done it. So no, processing uses single quotation marks. And you need to copy that over to Arduino. It turns out to be a very, very, very important thing. So Control T to line it all up, and we're gonna run it one more time. So remember to use single quotation marks. If you were printing it, single wouldn't work. But if you're reading it, for some reason, single and only single works. And line it up, click. Awesome. So see you in the next tutorial where we're going to edit this code to try to make it a Boolean, to try to make it so that when I press the button, the light sort of switches its state. That'll be a fun thing to do. Hello and welcome. So in this tutorial, we are going to be upgrading our click for a turn on the LED into a click for a change of state. Now, to do that, we're going to have to implement a system where, if you look in the screen right here, I've actually changed one thing. I'm printing that 0. Now, watch what happens when I click this. 0 changes to a 1, 1 changes to a 0. We need to write some new code that basically says either when 1 changes to a 0 or a 0 to a 1, we have a change of state. So this is not going to be so easy, but we certainly can endeavor to do that. As I said, new val and old val are going to be the key. We're also going to need a boolean, which is going to be light state. And we can set that to, oh, I don't know, on, off, set it to on, who cares? Okay, so here's where things get interesting. You see how we have that else here? We can do a switch from a 1 to a 0 or a 0 to a 1. I'm just going to go 0 to a 1. Doesn't matter. So we're going to need to have a nested if statement. So essentially, let's go like this. Just to make sure I've got a nested if. Control T. Beautiful. So if the light is 0, then we're going to check Control T. Then we're going to check if the light has switched from 0 to, sorry, if the state has switched from 0 to 1. And how do we check? Well, let's say this here is the new value. Now imagine this has been going on for a while. This is the new value. It's just been read. And we can have an old value which was read in the previous round. So the new value of this round becomes the old value of the next. So old val equals to new val. So if you just think about, we're doing a cycle. Right here, we have a 0. So now that's our new value. When we get to the next one, 0 is our old value. And this is what I'm talking about. So what we can do is if the old value was 0, if it was 0 before, and if the new value is 1, if it was 0 before, and if it's 1 now, so namely, like just watch. If it switches from a 0 to a 1, if that happens, then we can say something like this. LED state equals to the opposite of LED state. And we can even write LED val, comma, digital, right. LED val, comma, LED state. That ought to do it. Let's see. If Control T, am I missing something? Semicolon, Control T, old val. Oh, that just closes this if, so we need one more bracket. And the old val equals to the new val. Now, where does the old val switch to the new val? We are inside that if statement. The old val should switch to the new one right before the end. Yeah, I don't know. This, Control T. I suspect it could work. Why? LED state, but light state. LED state. Huh. Fine. LED state. Easier to change that than this. LED val. Wait. LED pin. What am I? Come on, man. Switch on. Okay. So there it is. It's uploaded. Moment of truth. Press play. Generate the thing. Alright. I'm going to do this like in front of the camera. No. Oh. Yay. Now, the secret is... No, it works 100% of the time. I have a feeling that like if you keep it pressed, no, I actually think this is, wait, that it doesn't work when your mouse isn't on, but I mean, you got 100% flawless execution there. So I'm actually really, really happy with my program, despite some silly syntax errors earlier. There you have a fantastic example of how you can basically send data from processing to Arduino and use it to change the state of the light. It's like a light switch in a house. Okay, in the next tutorial, we shall be bringing in this guy, an accelerometer gyro, and using processing to really, really visualize what the outputs of the gyro accelerometer are doing when we're moving it around. See you then. Hello and welcome. In this tutorial, we are going to plot accelerometer, yes, our good old friend accelerometer values using processing. And then we're going to actually also try to plot gyroscope values so we can really see the visual output of this sensor even more so than we did with the previous LED experiment. So to do so, there is actually an Arduino CCEN tutorial graph. There is some code that we can use there. It essentially gives you an example of, you know, like a voltage divider, and you plot that graph. I would go for something even better. I would take our code for the accelerometer and use that eventually. But first, let's just try to highlight this. Processing, graphing, sketch. I think this is where it all starts. That's where it ends. Control C. We put that into processing. We get our Arduino in here. And we work from there. So our port, like we've already done before, is going to be 1 right here. So if I upload this, all we need to do is print a single value, so we can print the value of the accelerometer X. I mean, this delay can be something very small. We can upload this, and it'll be very, very interesting. Question. N-A-N-N-A-N-N-A-N-N-A-N. Plot is at 9600. So there are no type string arguments, line 13. I really don't think we would need to print the serial list. Stop. Press play. Okay. I guess I would need to check if the accelerometer... we are typing the word accelerometer, and I think they just want to read a single numerical value. So we're going to try this thing again and see if this default graph produces a graph. Done uploading, play, and there you have it. Right, so you see I can touch that and the graph goes crazy. So I'm gonna have a look at maybe making this graph bigger, making our value something more meaningful so that the range is between 0 and 1000, because that really is. See, 1023, the height is mapped to 1023. This is the size of the window. So we can go in here, this being the width. I mean, I don't know how many pixels do we got. I can go maybe 1100, 1920 across. I reckon I can go 1100. And the height, I don't know, 650, maybe 11 by 7, like 711. Yeah, so we can do that first. Second, if I remember rightly, the values go all the way up to like 20,000. So to drop them to 1,000, you got to divide it by 20. You can just go AX divided by 20 or AX times 0.05. 0.05. That's like dividing it by 20. All right. So I'm going to upload this and see what kind of numbers I get. I'm looking for like, you know, 50s, 100s. No luck. That stopped. I may need to create a float that's going to be this. Oh, no, that's perfect. Okay, this could be too low, but we're going to see. We're going to have a look at what this graph now looks like. Nice, big. Okay. And it can go all the way to the top. That's what I was looking for. All right. So I was going to actually like calibrate it like I did before, like set it to 0, but I don't think that's necessary. And you can easily see, like, I can apply a little bit of force. It goes positive and negative, and you know, rather than going positive and negative, I think we can like ABS hit the absolute value here. Steady graph, and we can just apply some force. Right, left, and this only interacts on the x-axis, and x-axis is actually the right, left, up, down. It's the up, down axis. Up and down this way, not so much, but that way. That's where the force is being measured. That is pretty awesome. All right, let's see. I think the most interesting of all would actually be the gyroscope Z, which is the rotation axis. So we can like spin this guy and see what happens visually. And I already got an idea in my mind how we want to do this. So I'm going to not use an absolute value. So I've got to reduce the, I've printed that. So we're going to go for GZ. We're not going absolute. If we times it by 0.05, now we'll times it by like 0.1. And we're going to add 500 to it. Yeah, I think this could work. Let's see. So hopefully we're going to see a line going like through the middle of the graph, and then we can spin the guy. What is your problem, son? All right, looking good. Yes. Watch. Whoosh. Goes down to 0. It's pretty sensitive. It goes all the way up that way. And then goes down to 0. Up, down. Rotation. So we are going to stop there, and I think those are absolutely sensational ways to visualize the output of the accelerometer. In fact, I'll just show you one more thing. If you've ever seen a self-balancing robot, what you're looking at is, in a way, if you think the middle is 0, what you're looking at, the spikes down and the spikes up, that would be the motor output, which balances a self-balancing robot. the exact thing you're seeing on the screen is what happens inside a Segway, right? And the values that are being written up here and down there are the values that are being written to motors to stabilize the robot. So we are going to, in the next tutorial, see if we can do anything at all to smoothen that graph. But for now, that's everything. Have fun and see you in the next tutorial. Hello and welcome. In this tutorial, we are going to improve the visual representation of these gyroscope accelerometer readings. We're going to make it so that there are no crazy spikes. It's going to look just like this. And we're going to achieve this by using a moving average. Or not so moving average, we're going to take 5 values and then we are going to average them out. So just to give you an idea, by the way, in the last video, this probably should have been GZ here, but this is where we are starting from. And what you're going to see is that the signal seems fairly noisy. Right there, watch. So any type of slight touches lead to these crazy sort of spikes. And what we want to do is eliminate that and just have it sort of be a little bit more robust. So the way we do that, I think the simplest way to do that would be to have this reading done 6 times, 10 times, 20 times. We can try different amounts, and we can create a function with an that returns a long. So we could say get average, and inside this function, it doesn't take in any parameters, but it certainly puts them out. So inside here we can have a total, and a total can also be a long total. We can have the total can now be a sum of various readings. So total equals to total, and let's say we are measuring GZ here, GZ. So total is going to be total plus GZ, and the secret is to just repeat this. Let's say we repeat it 20 times, okay? If we repeated it 20 times, then we could return the average. You could say return total over 20, done. So all we need to do is put this into a for loop for int I equals to 0, I less than 20, I plus plus, open curly, close curly. So this is going to produce that total. We're going to return total over 20, and instead of printing anything complicated, we can serial print line, and we can just say get average. That's it. So we just call this function. So Control T, I think everything is in order. We should set total to 0, just in case. I'm going to drag this over. Yep, that looks fine. I think we can try this out. We may obviously have to multiply the this guy here by like a reduction factor of whatever we used last time. I think it would have been like 0.05 or something like that. But we can start right here. So let's see. Oh, it's gonna be way down, I think. We should make it return 500 plus, so we have that we have that there. Total, accel gyro, GZ. This should work. Let's try that. Oh! We don't need to get this reading every time in the loop, and somebody's gotta have a delay. Delay 1. So maybe just trying to get all of these readings as quickly as possible without a delay is what messed us up. But let's have a second look. That's much better. So it is hypersensitive, but it's virtually plotting a flat line here. So all I need to do is take this back into our multiplier, and I think, you know, times point. I don't remember, I think like 0.05. Yeah, 0.05 will do. Let's run this. My goal is that we just see a flat line when the thing isn't moving. It should be that capable of at least doing that. Yes, that's it. Perfect flat line. So turn this way, turn that way. And if you turn fast, you're going to go all the way to the top, or all the way to the bottom. Which makes me think, actually, if I can get this so easy, it could even be more sensitive. I'll try 0.02. And there you have it. I mean, that is a pretty good-looking moving average. No meaningless sudden spikes. So, like, ultimately the test may be to get some extra brackets around the total here, because the BODMAS may have tripped us up. Let's go. That's pretty neat. So, as you can see, with the gentle touches, nothing crazy happens. There was that one spike, but other than that, nothing. And I should be able to go all the way. All the way. And I'm wondering if we can simply swap this out for another axis, or for maybe the accelerometer. So you can try AX. Upload that. Let's see. Are we seeing a flat? Is it working? Okay. So that axis is definitely not the X. That one. I think up and down would be AZ. So I'm going to try AZ. And clearly, this level of forcing might have been suboptimal, but I think this is going to look good. Ah. What did I do? How did it get so huge? Divided by 0.05. Yeah, make it 0.03. And we can even average out more than 20 values. Maybe make 25. AZ actually includes gravity. Watch this. This is going to be interesting. Probably, yeah, it drops down to 50%. Right. That's gravity right there. Gravity. And now we can, and you can sort of see how powerful gravity is, because even the sort of shock, that the inertia of me doing this isn't as much as just gravity acting on it. That's pretty amazing. So there you have a much more leveled out, averaged sensor output. So we are going to be done with processing. I'm not going to do that much more than that. I hope that you guys can perhaps look in your own time inside the processing documentation, see what else you can do, play perhaps with the colors of the graph and the dimensions some more. And for us, we are going to go into looking at saving some data on an SD card in the future. So see you in those tutorials. Hello and welcome. In this tutorial, we are going to go back to our good old favorite, the human reaction time circuit, and we're going to blend it together with this, the DFRobot micro SD card reader with a micro SD card. I've actually got a huge one, 16 gig, basically about 1,000,000 times more memory than I need. Nonetheless, it's the one I happen to have. They work very simply. You click it in and you plug it into the blue end of the gravity shield. If you plug it in right, the lights go on, which it's really hard to plug it in wrong, to be honest. Bingo. Lights on, that's that. Program. Well, right here we have our reaction time circuit. I have moved the buzzer into pin 10. It seemed to be making weird sounds in pin 12. We will also try to do it without the buzzer at first, with just the light. And you're wondering how we're going to have the code which reads into the SD card. Well, it both is really simple and it isn't. We're going to use a standard data logger program from Arduino CCEN tutorial data logger. And what we're going to do is we're going to take this code and I'm going to run it just so you see what it does. After I run it, we're going to edit and merge it with the reaction time gain. So basically right here, we have the serial begins. It does all sorts of things. Initializing card initialized. It checks that the card is there, that the card actually is working, recognized, ready to write on. Then it basically goes from analog pin 0 to analog pin 1 and 2. So it takes 3 analog pins, A0, A1, A2, and reads the analog sensors, and then it adds them to this data string. And when it gets down to from 3 to 1, when it gets down to 1, it adds a comma and a new line. So this data string, this is sort of the key bit, and we can get rid of the rest of the loop and we can start to introduce this. But after I've uploaded it, what you're going to see is exactly what's going to be in the data file. We're going to look into the data file in the next video. But in this one, our goal is going to be to have 20 readings of reaction time. And then in the next one, we're going to open it up in a text file, paste it into Word, and graph it. So, you're going to, yep, that's it. So you can remove the auto scroll and you can see that right at the start it said initializing SD card initialized. So that's all pretty good. So right now we need to take this game, and I guess we can start with the variables. We're gonna skip out on the buzzer for now. LEDs in number 9. I guess button input, LED output. Right before the serial begin. Control T should handle that. And here we are in the loop. The data string is the most important component. This is the only thing we're going to keep. And we can delete all this. I suppose I can make a comment and just say our edit begins here. and our edit ends here. So we're gonna basically transplant our program into that area. And of course, we're going to be playing with it a bit. So for the interest of time, we're going to maybe wait between 2 and 5 seconds, make it a bit faster. LED high, that's good. Buzzer is out. Buzzer is out. LED low, your time was. Now, we can leave this in, but I would much rather, because what this does is it actually serial prints the data string once it's been written, and this will be interesting to see how long it takes to write the information in. The previous file was called data log. We can call this reaction result. So I imagine what would happen is that we're going to press that button, and instead of having an instant serial reading, we're going to have it like I don't know, quarter of a second later when the thing writes. So let's see. I'm of the opinion that we could probably get rid of all of that. So the counter is going to go to 0. Before the counter goes to 0, we are going to be adding to the data string. The first thing we're going to add to the data string, plus equals to, that's like data string equals data string plus equals to, the first thing we're going to add is going to be the counter. And we're going to, of course, convert counter to string. And the next thing we're going to add is a comma. So when we print the data string here, see how a data file print lines? It should sort of save it in a separate line. So it should be a result, comma, result, comma, result, comma. I'm not even sure that the commas are absolutely necessary, but I'm going to use them anyway. So let's see. Let's have a look at the way this displays. I really think we're good to go. LED high. Check here. We could have, So if we get that card initialized, then the start is going to be a big deal. That's good. So here we are, button circuit. Oh, that was pretty slow. And aha. Interesting. It's expecting data log text because I changed the name, right? File right. Let's try this again. Oh, yes. 18. And if you do false presses, it sort of reads it as 0, and zeros we have to ignore. So that works, and it works great. And it takes a little while to write to the SD card. Now, what I want to do is take exactly 20 readings. And one thing that I'm thinking is when this sort of starts, when our game starts, it should have the data string should write this, the game starts here. So we should write something like this. Plus equals to. So the data string should say that, and then we ought to do this little thing. $20 times. Let's try 10. I have a feeling that what's going to happen is that it's going to print out all the results as soon as we're done, which could work, So let's run it this way. For a loop or while loop. Now we'll do it a for loop. For int I equals to 0, I less than 5, I plus plus, begins, ends, begins, ends. So we're going to run it 5 times. And then the printing of the data string is going to happen after we do this whole game 5 times. Should be interesting. Good. So you expect to play it 5 times, and then there's going to be a printout of 5 results. And we can introduce a result inside here, and then follow it up with a printout as well. I think it's coming. Game starts here. 22, 19, 19, 19, 22, 19. That's nice. 22, 19, yeah. That's really good. If data file, because they're comma delineated, I don't even think I need the game starts here, right? I can just serial.print ln game starts. Next, I can say I want 10 results, and every time we exit this while loop, we can serial.print ln counter. And then it's going to print out all the 10 results, and those 10 are then going to be saved on the SD card. In fact, I'm going to have 2 runs of 10, and in the next video we're going to go into the SD card, have a look at the data log, and you are going to see exactly those 2 results. So let's do this one time. So we're going to play 2 games. Game starts. We're ready. 18. That was bad. 19. Good. 18. 20. Come on, come on. I think aha, there you go. That is the printout, and that's what we're gonna see in the next game. Oops, I think we just maybe cause a 0. No, let's go, let's go. That's my best time. Wow, backed up twice. I suppose practice makes perfect. 16. I've never done that well with light. 18. Wow. Oof. So there you have it. This and that should be saved on the SD card. And this kind of shows you that what you can have is serial monitoring going on and printing your own statements, whereas only what you add to this data string gets written into the SD card. So what you can have is save the crucial information while printing all kinds of other information to help the user play the game. So that is all for this video. In the next video, we're going to check out the data, then we're going to plot it in Excel, and after that, we're going to conduct a real investigation into sound versus light, and which of these two do humans, at least this human in this chair right here, reacts faster to. Okay, see you in the next tutorial. Hello and welcome. So in this tutorial, we're going to take the data we got from the little SD card. I'm putting it into an SD card adapter. Now these are cheap and widely available. I think I got this one at Kmart for $2 or $3. So what we're going to do is plug that into the USB and have a look at our data log, and then I'll show you how to produce graphs from that data log. So it just sort of jumps out. I try to save the data log as CSV. You can forget that. If you just open the data log, this is what you're going to get. You're going to get our little trials that we had. So it literally saved everything. And then the one game that we really did try. Game starts here. We tried 5 and then we tried 10 apiece. So let's just say we want to transfer this data to Excel and we want to make a graph. You copy and paste. So what you got now is just a bunch of comma sort of separated stuff. But if you go into data and if you go from text to columns, click there, delimited, click the comma, next, finish, done. One more time, text to columns, delimited, commas ticked, next, finish, done. Okay, so now you want to have like a graph of these two. Insert, click on the line graph, 2 line. Yeah, that looks good. Spread it out. So, Series 1 is my first attempt. Series 2 is my second. As you can see, I've actually gotten faster on average. I went I think consistently, and you can sort of hover over the spots, that one being 17. So the second one was consistently 17, 17, 16, 18, 16. So I get consistently better. So I suppose this here brings the theory of, do you get better with time or not? You can kind of select different kind of graph decorations, but this is not an Excel tutorial. So what we will do in the next tutorial is that I will take this code to work. Actually, I'm consulting in a school after tomorrow, and I will have a class fill in some data along with their age and whether they're a boy or a girl, and then we're gonna have a look at how you would deal with a larger volume of data with more attributes and what type of conclusions you could make from it. And after that, we shall conclude the course. So I'll see you in the next tutorial.